Good afternoon to everybody. We are good afternoon in Europe and morning in Latin America. We are waiting only for 5 minutes. How are you doing, Professor Silver? Everything is good with you?
Yeah, I'm here. Do you have a connection?
Yes.
I'm ready to share the screen as soon as you say.
Yeah, no worries. But before that you share your screen, we would like to make a nice introduction to your name, to all the person that is assisting to this talk, okay? Yeah?
Sure.
We will do it in both languages, in Spanish, because most of the people here is from Latin America, and the other one in English, to be able to understand what we are talking about to you.
Nice, thank you.
Vamos, Milton.
Buenos días a todos los participantes que hoy nos acompañan desde los diferentes rincones del mundo. En esta oportunidad tengo el placer de presentar a un gran matemático británico de origen ruso. Él es el profesor Boris Silver, quien trabaja con la teoría de modelos.
Good morning to all of the participants who are joining us today from different parts of the world. On this occasion, Milton and I have the pleasure to present to the great British mathematician with Russian origins, Professor Boris Silver, who works with model theory.
El profesor Silver obtuvo el título de candidato a ciencia en 1975 en la Universidad Estatal de Novosibirsk, el título de doctor Nauk en 1986 en la Universidad Estatal de San Petersburgo. Actualmente es profesor de lógica matemática en la Universidad de Oxford, a la cual se vinculó desde 1999.
Professor Silver received his bachelor in science in 1975 from Novosibirsk State University. I hope I did the correct pronunciation. And the PhD in 1986 from St. Petersburg State University. He is currently a professor of mathematical logic at Oxford University, whom associated since 1999.
Entre sus reconocimientos se encuentra el premio Berwick Senior Award del London Mathematical Society en el 2004. En el 2002 presentó Tarski Lectures, no sin antes haber sido ponente invitado en el Congreso Internacional de Matemáticos de Varsovia en 1983, la estructura de modelos de teorías categóricas incontables.
The Berwick Senior Award was from the London Mathematical Society in 2004. It's one of the most famous recognitions that Silver has. In 2002, he presented Turkish lecture, known before having been a guest speaker in the International Congress of Mathematics in Warsaw in 1983, which the name of the lecture was The Structure of Model of Uncountable Categorical Theories.
El profesor Silver obtuvo en 2004 un resultado en teoría de modelos de fundamental importancia para la todavía incompleta hipótesis de Chamuel, de gran importancia en la teoría de los números trascendentales. Con Ehud Hrushchevsky, disculpe ahí la pronunciación, introdujo la geometría de Zariski, generalizaciones de la topología de Zariski, y esos temas fueron compilados en su libro Zariski Geometries, geometría desde el punto de vista del lógico, publicado en 2010 por Cambridge University Press. También es conocido por por la hipótesis con Gregorio Charlin en teoría de modelos, explicada por él en 1977, hipótesis de Charlin-Silver.
Professor Silver obtained in 2004 a result in model theory of fundamental importance for the still incompletely Shanwell hypothesis and the theory of transcendental numbers. Together with Herod Hurowski, he introduced Zariski geometry and generalization of Zariski topologies. Those topics were compiled in his book, Zariski Geometry from the Logician's Point of View, published in 2010 by Cambridge University Press. He is also known for a hypothesis with Gregory Cherlin in model theory, explaining by him in 1977 Charlotte-Silver hypothesis.
Con este pequeño resumen, doy paso al profesor Silver para que nos cuente un poco más sobre la teoría de modelos y sus aplicaciones.
Now, Professor Silver, can you inform us more about model theory and its application, please?
Thank you very much for this very nice introduction. I'm very happy to join you for this conference and share some of my most recent thoughts about model theory and some prospects of what the current developments could lead us to.
Oh.
Let me share the screen. Okay, I should say share and does it work?
Yes.
Hello? Do you see me?
Yes. It works.
Yes.
Okay, then I can start. Right. So I'm going to discuss some results and trends in what people often call applied model theory. Although I must say that model theory from its inception was always actually applied, and from time to time some of the results in model theory could be characterized as pure model theory, but then the most interesting ones take you back to some applications. And specifically, I'm going to talk about the aspects of model theory which are not first order. Just to give you a better idea of what I'm going to talk about, let me once again read these few lines that there had been a gradual shift from first order model theory, a very developed part of model theory, to its non-elementary versions. This had been driven by discoveries both of new model theoretic notions and constructions, and also discoveries of new applications in number theory and algebraic geometry that I would be most interested in. And I will discuss one such development. It is the notions of categoricity and stability of abstract elementary classes. So these are the classes which are not first order axiomatizable. And with this new, maybe can say, shift of paradigm of how we do model theory, a connection is being developed to analytic aspects of algebraic and arithmetic geometry. And this is the most exciting part of these developments. So once again, the notion of elementary first order theory in this development is replaced by a notion of abstract elementary class, about which I'm going to say much more. And a standard notion in first order theories, the notion of completeness, is actually not applicable in non-elementary logic and non-elementary model theory. One of the main reasons is that it is not always possible, and maybe it is the rare occasions when it is possible, that in non-elementary context you can have a deduction system. And in the context of abstract elementary classes, you are not supposed to have one. So the notion of completeness very naturally here has to be replaced, and the natural replacement is a much stronger notion, and this is a categoricity. And what I'm going to talk about is always a categoricity in uncountable cardinals, or well, assuming that we work in the language with of countable signature, then it is just enough to say that the cardinality of models that we are interested in are uncountable. And once again, it turns out that the examples of interest in this context are, well, turn out to be of analytic nature. And the mentioning of applied model theory in my title means that I'm not so much interested in pure model theoretic aspects of these developments, but rather the analysis of how it is linked to mathematics as a whole. And it turns out that the most interesting examples that this story is relevant to are of analytic nature. Okay, so a bit more detail now. That I'm recalling that the formal theory, which we think as a set of axioms, is said to be categorical in cardinality kappa if it has a unique up to isomorphism model of this cardinality. And it approximately in 1965, when Morley's paper appeared, we in model theory started to understand, to realize that the key property of model theory, sorry, a key property of a model of a categorical theory is that there is a good notion of dimension of definable sets. So technical notion for this was mole rank. And then later on, we discovered that this notion fits very well with examples coming from algebraic geometry, and in algebraic geometry it is called dimension. And then there are other rank notions that were introduced, a lot of them by Scheller, and they were called also ranks of different with different specifications and degrees, this sort of things. And as I practically said already, it is that the typical example here is that we work with algebraically closed field. So our model is a field with addition and multiplication. So we can perform this operation on this universe and write properties of elements and define in this way the sets of elements. And when we define some such set, let's say it is a zero set of some system of polynomial equations, we can define it in the structure. And then we have the standard notion of algebraic geometry, basic notion of dimension of such a set. And the dimension is zero if it is just a finite set. A dimension is one if it is a curve, and in this example it is would be called an algebraic curve. And dimension is two if it is a surface, and so on. In fact, the most interesting examples and examples that inspires this theory, they come from algebraic geometry. And so in this regard, one can think of this first order categoricity and stability theory as a sort of abstract extension of algebraic geometry. And the technical notion that is a natural notion in this model theoretic context, the notion of stronger minimal set corresponds to an irreducible algebraic curve. And alternatively, the fact that it is irreducible can be expressed in this form. So it is something of dimension one, such that any, you actually doesn't have to say in this case that it is of dimension one, just to say that it is infinite definable set. And then you say that every its definable subset is either finite or complement to a finite set. So this is a very simple way, very abstract way also of characterizing algebraic curves, irreducible algebraic curves. Now, Kiesler, Scheller, and others explored extensions of Morley theory to non-elementary languages, say languages with infinitely long conjunctions and disjunctions. And one of the languages of interest to us that I'm going to mention further on is this language L omega 1 omega, and these subscripts here mean that this is a language where we allow conjunctions and disjunctions of countable lengths. And when we use quantifiers such that for all and exist, we apply them to only finely many variables. Right, so it is some technical definition, but for some quite good reason, it turns out to be a very useful language in our context. Well, it turns out, and this was a big new idea and new understanding that it is better not to look into specifics of the language of these non-elementary languages that you are using, but rather use this idea that was expressed in the definition of abstract elementary class, which we define an abstract elementary class. We define as a class of abstract algebras in certain signature that as a class it has certain properties. So, for example, the union of the increasing union of models in this class, the union of this is again a model in this class, and similar things. And with this, Shelah showed us how to extend Morley theory to a very wide, to a variety of new examples. I mentioned Kissler here. Kissler actually started going in this direction, but he missed this point, and his contribution to the field is quite significant. But this idea brought us much further. And the notion of a quasi-minimal set here is to replace here a notion of strongly minimal set. And the definition of quasi-minimal, which I guess is going to be a bit more detail, you will see in the next page. But let me say it here. So instead of strongly minimal, when we define strongly minimal set, we say that every subset of it is either finite or cofinite. And here we are saying that every subset of it is either countable or complement to a countable set. So it is very similar idea, and this idea. So again, you should think about a reducible curve, but as a main example. But now it is not an algebraic curve that we should imagine in this case. It is more like an analytic curve. So the idea of this extension, this new model theoretic idea working well with in analytic context is already here. and here is the prototypical example of what can happen, what sort of abstract elementary classes, and indeed very nice abstract elementary classes that eventually can be L omega 1 omega axiomatized. So it comes from this relatively new example, the example which was for some good reasons not considered in first order context. So the example of very natural structure, so you think of a complex number as a field, so you have addition and multiplication, so you have all the notions of an algebraically closed field. And on the top of this operations, you also have an operation of applying exponentiation to a complex number. And of course, now you can express much more in your language. And so, for example, you can say that your complex number z is such that exponentiation of z is equal to 1. And then this complex number has to be of the form 2 pi I times times an integer. And in this way, it is easy to define a ring of integers sitting inside here. And of course, the ring of integers is very complicated and undecidable object in first order context. And this is a reason actually why people didn't dare to try and do any deep model theory investigation of this structure. But in the context of L omega expressions, it makes sense. And the natural conjecture here turns out to be this one, that we can write down some L omega 1 omega sentences characterizing the structure so that any model of this is defined, well, any uncountable model is defined uniquely up to isomorphism if we also fix this uncountable cardinal. And the whole thing here, the universe would be seen here as a quasi-minimal set, or as we already discussed, as some sort of irreducible analytic curve, or if you want, an irreducible complex manifold. Okay, so this is still a conjecture. So now some 25 years old, and it's open. Here I reminded you what quasi-minimal means, and here is what we managed to prove with a lot of work. So it turns out that although we cannot answer this particular question that is being posed by this conjecture, we can say something quite interesting about this sort of structure. And this is the statement that we can be sure that we can construct an algebraically closed field K with an operator which has all the properties, all the algebraic properties of exponentiation, and in fact all the properties that we expect from this exponentiation that can be written reasonably. And this structure, so this artificially created structure does satisfy what we expect of this structure. So it's L omega 1 omega theory is quasi minimal and categorical. By the way, most of the time I'm omitting mentioning that my categoricity means uncountable categoricity. Okay, so in fact, it is, as you see, here is a date when the process of proof started, then and the proof initially was split into 3 papers, and then it took a while to fix some gaps in these papers, and so the final the point in this process was in 2015. Okay, and so this is the beginning of the story that I'm going to tell today. I'm not going to talk about this particular result, but rather some developments from that started from there. And it is important now to say a few words about the proof of this result. So first of all, and naturally, it is the pure model theory ingredient in this proof, and this is quite important, was this Shalach theory of abstract elementary classes, enhanced by this theory of quasi-minimal geometries. It's quite interesting that when Shalach wrote his main papers about abstract elementary classes and categoricity, by the way, there are still some beautiful open questions in this difficult open questions in this area. So probably because he wasn't so much interested in geometric examples, he didn't make any comments on the possibility of extending this notion of strongly minimal set and strongly minimal geometry. And so this came in the course of proving this particular theory. A very important ingredient here was also Hrushevsky pre-dimension theory, which came from a different development. So this is a development in first order categoricity theory, where Hrushevsky introduced ingenious construction of non-classical categorical or strongly minimal structures. And so what this theorem, this proof that I'm now discussing with you, demonstrated that actually Hrushevsky pre-dimension theory tells us a lot of tells us a lot about behavior of transcendental functions such as exponentiation. And in fact, Hrushevsky pre-dimension theory can be interpreted as a huge generalization of a classical Shanwell's conjecture from transcendence theory, which, of course, Shanwell's conjecture, which was later recognized, was actually so Grothendieck formulated much more general period conjecture, and André he extended this Grothendieck's period conjecture. So Grothendieck-André period conjecture is in a way equivalent of Hrushevsky pre-dimension theory of in the context of algebraic geometry. My conclusions, which with which I'm going to finish today's talk, do not mention directly this connection with period conjectures, but because I'm not talking about these aspects of this theory, but in fact it is also part of a very important part of this story, and this story of connection to algebraic geometry. And finally, the third part of the third ingredient of this is are some very important results in arithmetic geometry. So in this case, in this particular example of categoricity of abstract elementary class, what we really needed to, what sort of arithmetic facts we needed to, so it is some classical, actually it is end of 19th century results on Galois action on torsion points of the torus, well, GM. So it is the field, the multiplicative group of the field, and so torsion points of the multiplicative group of the field are roots of unity. So how Galois action, Galois acts on roots of unity? Yeah, I think it is Dedekind results. Then it is extension of Galois theory, this Kummer theory. So it is more specifically how Galois theory applies to this sort of multiplicative group. And then there is a version of, again, the version of Mumford-Tate conjecture. I'm not going there, what it means, but it is a conjecture that is applicable to this specific simple situation. But it is quite substantial results in arithmetic geometry. Right. So one of the ingredient in this proof is a consideration of a more simple structure, and this is so this is still the structure that works with the same notions, but it is now separated. We separate the field of complex numbers as a domain of exponentiation, and the multiplicative group, this GM, is a target of exponentiation, and in this context, and that's what in algebraic geometry people would call it, exponentiation serves as a covering map. So this is some algebraic curve, and this is its covering space, and this is a analytic covering map. And this situation can be repeated in many other important examples. Well, as a matter of fact, we are interested here in so-called universal covers, if we speak about general context. And universal cover makes this picture a little bit more interesting. So what you see that we insert here sort of intermediate covers. It is easy to see that if we start from another copy of the multiplicative group of complex numbers and we apply this map, then we end up in the same multiplicative group, but now we will have what would be called a finite cover, or cover of order n. And we can do it from with different n and m, and this cover is universal because it filters through all these finite covers.
So we want to write, Boris, is GN, the one on the right, GM or GN there.
No, it is GM because M, it is not the number.
Yeah, okay.
Yeah, it means multiplicative.
Okay.
Yeah, so it is a name of the classical name of naming of such an object. Yeah, because they all, in this case, all the covers are isomorphic, but the maps are different. Okay, so this is what I shown here is a typical example, and as I said, it can be repeated with, for example, elliptic curves, and if you work with elliptic curves, then the cover would still be the same. But the object here now is not this group, but so-called the group on elliptic curve, and we will talk about this example. Now you see, as an ingredient in this initial theorem that we talked about, actually, there was a proof that such a two-sorted structure is also categorical. It has some natural system of axioms, and this gives us this categoricity of this two-sorted structure. And what is important is that so this is a simpler task to prove, and as I said already, to prove this statement, we do not use Hrushevsky construction, and so we do not mention Chanel's conjecture and similar. What we are left with, so we have a specific version of this theory of abstract elementary classes, and we need this arithmetic, all the arithmetic arguments, arithmetic results. So it is we sort of focus here on the more specific aspects of this situation. And this situation is easier to study in many more examples. So here is the next example, and you see that instead of this multiplicative group, we considered the elliptic curve, and the statement is for arbitrary elliptic curve. well, in 2012, it was elliptic curve without complex exponentiation, but now it is known for all cases. Now you see, again, we need certain arithmetic facts, and this time these arithmetic facts are a little bit more difficult. Well, actually, quite considerably more difficult. So this Bashmakov extension of Kummer theory actually happened sometimes. Kummer theory, it is beginning of 20th century. And Bashmakov got his result, the result that we needed sometime in 1970s. And then there is a very important and difficult Serre open image theorem instead of this Dedekind theorem. So quite essential arithmetic facts are linked with this theorem. Then there are similar but less complete results about abelian varieties. And in this case, we required the arithmetic facts that we require. It is Ribet and Larsen theory, and this is 2010, I think, that the result that were used here. So it is quite advanced arithmetic that we have to use here. And then a very recent result. It is by Chris Doe and myself. So it is the first result. It is based on a previous result of Adam Harris, my student at the time. So it is the first example where the covering space is hyperbolic. So it is hyperbolic example. And hyperbolic examples are more complicated and more interesting. And again, it requires some quite advanced and quite recent facts from arithmetic. Right. And also what is very important is that not only we use these arithmetic facts, but we can also prove that these arithmetic facts are necessary. So in other words, that assuming that the natural theory is categorical, the arithmetic facts follow. So you see the statement that this certain L omega 1 omega sentence has a unique model in every uncountable cardinality. So this is very abstract statement, and it implies strong arithmetic results, facts. By the way, I said that in all the previous, well, this is, except this one, I mean, this, it is not the content of this theorem that we can prove yet. But in general, the belief is that it should work like this every time. Okay. This is all encouraging and inspiring, but every time, every case study that we do becomes harder and harder. Well, simply for the reason that you have to learn a lot of deep algebraic and arithmetic theory. And it is not very clear whether it is the right thing for a model theorist to do, to go into deep waters of someone else's profession. So let's go back to model theory and think of of a big picture. So what we are doing here? We have several case studies, and now a couple of questions. So the first question is, of course, how general this phenomenon that we discovered in this case studies can be. Can we even conjecture that every time we consider this sort of a cover structure of an algebraic variety, it can be L omega 1 omega axiomatized by some natural axioms, so that it gives us a categorical abstract elementary class. So this is some natural question to think about, and the second question is whether we can seriously hope that model theory can somehow impact arithmetic geometry, or well, in fact, it is not just arithmetic geometry that we study here, but also sort of analytic aspects of, so this is arithmetic geometry related to analytic aspects of algebraic geometry. Can model theory be really useful here? So these are natural questions, and there have been little progress now here, and so here is a very recent result. A slightly simpler version of this is on arXiv. And this slightly simple version also is submitted to a journal. Okay, so let us look at this situation. So we have a complex algebraic curve, which we also assume to be projective and smooth. And such a curve will always have a universal cover. This is this one, and then and there is this covering map, which is something similar to this exponentiation or some hyperbolic functions. Yeah. So so what this theorem says, that in this generality, we cannot say we axiomatize this, but we can say that we can construct a categorical abstract elementary class for which this is one of the models. And categoricity means that if you are interested in the same categoricity as the categoricity of complex numbers, then every other model in this abstract elementary class is isomorphic to this picture. But also it says that you can have the same picture in any uncountable cardinality. So it is abstract elementary class, every model of which looks exactly like this one. And so here you would have always some algebraic curve over some abstract algebraic closed field of characteristic 0. So both sorts are quasi-minimal. So this is what this theorem says. Well, similar but weaker result holds for arbitrary algebraic variety. So here we assumed that this is a curve, So what about surface or n-dimensional algebraic variety? And this is what we are talking here about. So it is possible to have the similar result, but the categoricity can only be proved. I can prove this categoricity only for cardinality Aleph1. And so it is an open question of how to lift it to arbitrary cardinality. And this is a challenge of purely model theoretic kind. Now, the proof here, the proof of this theorem is based on it is quite unexpectedly it is based on O minimality. So O minimality is another very important in development in model theory that is used now specifically due to some groundbreaking results by Pila and Wilkie, used a lot in arithmetic geometry, like Andre-Oort conjecture and yeah, there is also something that is called Zilber-Pink conjecture, and part of it is also the Hodge conjecture. I mean, part of this developments, and quite unexpectedly, the technology of minimality, actually very basic technology of minimality, the technology that was developed by Peterzil and Starchenko. Not too much is used in the proof of this theory, but it is the first time that such a deep connection between O minimality and categoricity shows up. You see, categoricity is a stability phenomena, and O minimality is, in this regard, it is well, O minimal structures. The interest in O minimal structures is unstable by definition, and the interaction between these two is quite interesting. And there is also some link to at least the thinking behind this is a bit similar to the thinking that is being used in Pila-Wilkie approach. Right. So I think it is, at least for me, it is quite interesting direction to look further into. And as I explained already, the proof is quite simple compared to these case studies that I illustrated my talk with. So no arithmetic information is required for this very general result. And no L omega 1 omega axiomatization comes out of this theorem. So this theorem simply says that there is a categorical abstract elementary class that that this is included into. But how this class axiomatized, the theorem doesn't tell anything. And so there is a obviously open question. Can this sort of abstract elementary class that we obtained in the previous theorem, can such a class always be axiomatized by an L omega 1 omega sentence? So are there arguments that give us such an L omega 1 omega axiomatization? Right. So now let me use the last of this slides, a long slide, to make to think aloud about what is going on here and whether there are some interesting promises here. So the object that we study here, the covers, the universal covers of complex algebraic varieties, right? That's what we are looking at. And by its very definition, this the notion of universal cover is topological in nature. Well, topological and analytic. So we have seen that the object is that appears there are some interesting analytic functions, classical analytic functions. Now, when we ask about L omega 1 omega axiomatization, we must take into account that the very nature of this language. Remember, so what is this language? We use as just usual sort of algebraic relations. In terms of usual algebraic relations, we build a sentence that can have, kind of incountable steps. We build such a sentence, and by its nature, such an axiomatization is characterizes this this object, the structure that we're talking about, in this discrete and also in algebraic terms. So so we have here some contraposition between this topological analytic and discrete algebraic terms. And this is actually brings us close to the thinking that comes into basic the key conjectures in algebraic geometry. First of all, this Hodge conjecture. So what actually Hodge conjecture states in very general terms, it states a conjectural equivalence between certain topological notions that are well, exactly of this kind of topological notions, and algebraic notions, some algebraic cycles, some such things. And of course, this Hodge conjecture is formulated much more concrete than the terms that I'm using here. But as you see, we can the question about L omega 1 omega axiomatization. Its advantage is that it is very general. The way that it formulated it is much more general, and also as a case study showed us, in fact, the amount of arithmetic information that goes into it when it is sorted out in cases when we have a definitive positive answer to this. So it delivers much more information that is just the Hodge conjecture. So, but of course, again, this depends on what exactly, what form of this concrete axiomatization, concrete L omega 1 omega sentence we can deliver. yeah, so it is what we have done. It is a step in this direction, and yes, so maybe that's all that I have to say. And yeah, I finish with this. Sorry, it is exactly 1 hour that I talk. Thank you.
Thank you very much, Professor, for your presentation.
Has someone questions? If someone
Right.
has question, please write it that we can make the translate, sorry.
I have a lot of questions. Boris, hello. Yes, can you hear me? Sorry.
Yes, yes, I can hear
Yes.
you. Yeah.
Yeah, you know, unfortunately, there was a problem of construction noise in the last part that was incredibly interesting of your lecture. But allow me to ask the following question, because in a way, with your last result, you seem to be moving away from the original framework and going to O minimality, or a kind of a abstract elementary class version of O minimality that seems to be wandering away from categoricity a little bit and exploring the map of all possible, abstract elementary classes in different ways. Let me just say one thing. L omega 1 omega axiomatizable AECs are one important but one small part of all possible AECs. Maybe your phenomenon and your last question on the topological analytical kind of category versus the more discrete given by L omega 1 omega may be related to other parts of AECs. Do you see any role for the classical conjectures that drive all the classical conjectures you've been mentioning a little bit here, like period conjecture or standard conjectures and so on, for maybe in some situations being of a more, I don't know, AEC nature, but not necessarily L omega 1 omega. How specific is L omega 1 omega, or how central?
Yeah, thanks for the question. By the way, I should have mentioned in the beginning that the idea to go into this direction. So this abstract elementary class that I mentioned here is a projective class. So it is you start with creating some axiomatized class that uses or minimal language, and then you take projection of this. And I learned about this projective classes listening to Andres talk about Andres and Schellach's result about projective categoricity. So I should have mentioned this. Yes, well, you're right that it is not it is not maybe canonical to refer to L omega 1 omega, but the choice of the formulation, the reference to L omega 1 omega, it is, well, it seems to be a simple choice. Maybe one can, well, one probably have to be more specific, or maybe look for a better choice of what exactly your language. But you see, in this case studies, if you look back into the formulation of this, I mentioned that that the L omega 1 omega axiomatization there was natural axiomatization. So it is not just some L omega. We don't know whether there is some L omega 1 omega axiomatization. Let's first try and answer this question. And if we can answer this question, then we can more specifically ask about natural axiomatization. And what natural is another very interesting point of
Yeah.
discussion.
Yeah, that might be crucial also to your connection to, these conjectures and so on. Allow me just to mention very, very quickly that in the past 2 years, a lot of new lines have been opened or are being opened toward finding the natural logic of an AEC in general. It may be L omega 1 omega in many cases, and I think it is a very important subcase. But finding the natural logic of an AEC is now, we now know a little bit more. We still have many questions, and maybe your examples may provide a lot of driving, intuition for that question. So that's an interesting thing also. Thank you.
Yeah. Interesting.
Someone has more questions? Remember that you can raise your hand and we can give you also the space to use your microphone. Yeah, we have someone that raised the hand here.
Mhm.
Okay.
Okay, Tanya can unmute by herself.
Yeah.
Hola, quería saludar a profesor Zilber porque tengo mi doctorado de la misma Academia de Ciencia con el profesor. Con su permiso, sí. No sé cómo en inglés mejor. Jessica,
En
¿cómo
inglés,
hablo?
por favor. Ajá.
In English. Should I make it in English?
Yes.
I would like to salute the Professor Silver because I defended my PhD in the Computational Center of Novosibirsk, in Академгородок.
Yes. Nice.
Здравствуйте.
Nice to see you.
Вот. У меня ведущая организация была Институт вычислительной математики и математической геофизики Сибирского отделения Российской академии наук. It was my leading institution of Institute of Mathematical Geophysics and Computational Mathematics of Siberian branch of Russian Academy of Sciences. I would like to appreciate your talk very much, and I'm a Kolmogorov guy. I would like to mention that we all thought, well, the probability theory and statistics don't need the axiomatization, but then Kolmogorov came with axioms, and then he gave axiomatization of what a probability function would be, and he called them axioms, and then I'm this point of view, but it's not my area of research at all. I'm so sorry. Thank you very much. Bye.
Yeah, thank you. Very nice. Yeah.
Nicole, I saw Nicole also raising the hand.
No, excuse me.
Okay. Okay, perfect. Professor Silver, before to finish this conference at the moment, this talk, someone wants to say to you some nice words. You know him, it's your colleague and friend, Andrés Villaveses. He wants to say to you something. Then go ahead, Villaveses.
Oh.
Well, I already said things. Of course, we are extremely thankful here to you, Boris, for bringing all these subjects and all these connections between our dear logic and our dear mathematics that is, much wider than logic as we know, but that may, that as you have already uncovered, has really connections very deep, at both in the sense of logic and in the sense of mathematics. So we look forward to more and more developments of all of these connections. Thank you very much for being here and bringing all of these things, Boris.
Thank you very much for your very, very nice nice words, and thanks for the invitation.
Thank you for being here.
Yeah, thank you to Professor Silver. We are really, really happy to have you here today and hear all your talk. Yeah. So for all the participants, remember we have the next talk in 1 hour, 11 a.m. Colombian time and 6 p.m. Central Summer time. Okay, European Summer time. Remember that. Yep. Then see you in 1 hour with the next talk that is for Manuel del Pino. Okay.
Yes. Okay, thank you very much.
Professor Dos Santos. Finally, how are you?
Hello, thank you. And you, how are you?
Very, very happy to have you here.
Thank
Professor,
you. Thank you for the invitation.
It's our pleasure. Let me see if Professor Julio Delgado.
Yeah.
Okay, so Professor Julio Delgado now is co-host.
Okay. Hello.
Hello.
Hi, David. How are you?
Good, good. And
Yeah, I
you?
was taking care of something, but now it's fine. Yeah. Okay, then. So how is everything there in
Good, good. It's a
Lorraine?
little chaotic, but
Yeah.
I'm managing.
But now you are at home, I guess, right?
Yeah, I thought it was easier because if not, I had to
Okay.
come back from the university, and so better
Okay.
do it at home. You might have some dogs barking at some point, but I'll try to.
Yeah. Okay. Let me increase the volume here.
I should share the screen, no? Oh, yeah. Good. Oh. Yeah.
Bravo. ¿Cómo va todo?
¿Qué tal,
Hi,
profesor?
Mario.
Yo, Julio. ¿Todo bien?
Sí, ahí ya estamos listos aquí. Ya le escribí a Raúl
¿Escribiste a
para
Raúl?
esta otra cuestión.
Sí, no
Ok.
creo que haya problema. ¿No? No es importante que estés aquí.
Sí.
¿Todo bien, Duván?
Profesor, todo muy bien. Muy bien,
Ok.
gracias por hacer toda la gestión con los links.
No faltaba. Para eso estamos. ¿Qué, Brian? ¿Cómo estás? Ahí escribió Brian. No, de eso se
buenos
trata.
días, Brian. Sí.
Muchísimas gracias a ustedes. Más bien.
Okay.
Okay, so we are waiting. Just
So maybe wait a couple of minutes.
6 minutes. It's 10:54.
So we also have Daniel Campos from Costa Rica.
Hola, hola. Good morning to everybody.
Hey, good morning, Daniel.
Hi, Daniel.
Thank you for organizing this. I went yesterday to the talk by Terry Tao and by Professor Toro, and both were amazing. Yeah. So thank you for putting this together. It is a marvelous group of people that are speaking today. So
Thank you very much, Daniel. So now we have the opportunity of hear Professor Dos Santos, tomorrow Professor Koenig, Professor Donaldson, and many interesting mathematicians.
Can you see the hand in the when
it's moving.
I can use it as a pointer.
Yeah, it's moving around. Yeah.
Good.
Okay, maybe we can start. So today we have now this the plenary talk by Professor David dos Santos Ferreira from the Institut Lee Cartan Université Lorraine in France. So Professor dos Santos Ferreira did his studies in mathematics at the École Normale Supérieure à l'Université de Rennes. His field of expertise is the analysis of PDEs. So Professor David dos Santos Ferreira has held visiting positions in some of the most prestigious institutions for research in mathematics, as the Institute for Advanced Study, Mittal-Leffler Institute, Mathematics Science Research Institute, Fields Institute. Some of his main contributions focus on the Calderon problem, Kahneman estimates, which is one of his topic today, and applications to PDEs, with some of his publications in collaboration with very well-known mathematicians as Carlos Koenig, Gunther Ullmann, Johannes Jostran, among others. So I had recently the pleasure to visit him in Nancy in August for some days, which is a very nice place with a lot of history, mathematics, Poincaré, Laurent Schwartz, Cartan, many others. So it's very interesting. It was a very nice experience. And as I said, it's a very great pleasure to have him today. And we thank David again for accepting this invitation to participate in this event, which is very important for our mostly for our Latin American community, but this worldwide broadcast. So so thank you, David. And then we have his lecture, which is entitled On Global Kahneman Estimates in Lebesgue Spaces. So thank you, David. And then you have the now well, almost 1 hour to speak about your topic.
Thank you, Julio. Thank you very much for this very nice and friendly introduction. I would like to thank the organizers of this conference for inviting me to give a talk. Actually, it will be my first talk by distance on Zoom. I have been teaching during the COVID, but I have never given talks on Zoom. So that's a premiere. I would like to talk a little bit about Kahneman estimates. And so the first part of the talk will be sort of a general description of what I intend to do and what are Kahneman estimates. And the second part might be a little bit more technical, but what I want to do is to focus on the techniques to derive Kahneman estimates. Yeah, so this is based on a joint work with Rémi Buff, who's also at the Institut Lee Cartan de Lorraine. And let me start by saying, so I don't know exactly how familiar people in the audience are with Kahneman estimates. So I will start describing them a little bit and say a few words about applications also and why they are interesting. So what do we usually mean by Kalman estimates? Let me just... So they are a priori weighted estimates of the following form. So you're controlling a function by a source term, which is in. So I should describe a little bit what I mean by the different notations I've been using. So P is a differential operator typically on a manifold, on Rn or on a manifold. I will be interested on compact Riemannian manifolds with boundary. H is a small parameter which is intended to tend to 0 at some point. And the important thing about those estimates is that the constant C is uniform with respect to the parameter. So particular attention is given on the dependence with respect to the parameter H. And then these are weighted estimates. So weighted in the sense that an exponential weight, which where phi is a real valued function, generally, let's say positive or with a sign, so that you see that when H tends to 0, the exponential is growing. And is a way of measuring somehow the exponential behavior in the problem. And then X and Y are typically Sobolev spaces, which are constructed on either on L2, and these will denote by L2 Kalman estimates, and the ones I'm interested in will be Sobolev spaces, and by Sobolev I mean mainly Lebesgue spaces. So the constant, of course, is also uniform with respect to U, and U is a smooth function which is compactly supported the way I've written them in the interior of the manifold. So they vanish at the boundary so far. But in the second, in a second one I will explain is that by global estimate, I mean also estimates where the test function U can have non-zero values at the boundary, or rather can be not flat at the boundary. So they were introduced in 1939 by Kahneman, and they were derived to prove unique continuation properties of solutions to partial differential equations. And since then, they have found many applications, in particular in control theory, also in inverse problems, and more generally, all sorts of problems related to PDEs, in spectral problems also, resolvent estimates, things like that. I should say just a few words about the unique continuation. Why is this interesting for unique continuation? So suppose that you have a solution to the PDE, let's say an elliptic like the Laplacian U equals to 0, and you want to prove that if the solution vanishes, let's say on an open set, it vanishes globally. So what you can see is, of course, since the Kahneman estimate is true only for compactly supported function, you cannot directly apply the estimate to a solution of your PDE. You have to use a cutoff. And when you use a cutoff, on the right-hand side term, commutator appear, and the commutator localizes the right-hand side term in the set where the cutoff equals 1. And usually in the proofs of unique continuation, you construct the phase phi and the cutoff in such a way that you gain more exponential decay on the right-hand side than what is expected, given that the left-hand side has to be 0 close to a point. Okay, so it's this typical argument where you cut off and you use very subtle construction of the phase phi and the cutoff in such a way that on the right-hand side, this gives you exponential decay. So I won't say much more about applications to unique continuation. I will be interested in those type of estimates for themselves. Okay, so some general remarks. How do you prove such estimates? So the first step is, let me go back to the first step is to change the function u and take into account the exponential. So if you denote v equals exponential phi over hu, u is exponential minus phi over h v. And if you look at the right-hand side, this will conjugate the differential operator by the weight. So you will obtain an estimate. You will try to prove an estimated on the conjugated operator. And it's very easy to compute the conjugated operator. It's just the Leibniz law. It tells you basically that the differential operator is shifted somehow in the frequency variable in the complex part. So here I'm using a semi-classical convention, and this is due to the fact that since you want to obtain estimates which are uniform with respect to the parameter, you have to think that 1 over h, which is large, is a little bit like a derivative. Okay, so you have to think as this parameter as, let's say, if you were in the Fourier, if 1 over h was the dual to a Fourier variables, that would be like a derivative. Mm-hmm. So this is why I'm putting the h with the derivatives. So that is the first thing. And now you look at the operator p phi, and using this semi-classical convention that you have to take into account the parameter h, you see several things. The first thing is that even if you started with a self-adjoint differential operator, like the Laplacian, you end up with something which is non-self-adjoint. Because of course, if you take the adjoint, this exchanges the two exponential and changes phi into minus phi. Okay. So the adjoint of p phi is p minus phi if p is self-adjoint. Then you can look at the principal term of your conjugated operator, which is the principal symbol, again in the semi-classical sense. So you have to take into account the fact that every time that the parameter 1 over h appears, it counts like a derivative. And what you see is you obtain this function pxc plus id phi when small p is the principal symbol of capital P. So again, you see that the operator is non-self-adjoint because the principal symbol is complex valued, has a real and an imaginary part. I did the small computation of what you obtain if you take for small p the symbol of the Laplace operator in the Euclidean space, and you see that you obtain something with a real and an imaginary part. And more important is, even if you started with something elliptic, your conjugated symbol is non-elliptic, has a characteristic set. For instance, in my example, the characteristic set is norm of psi equals norm of d phi, which localizes in a sphere in the psi variable, and psi orthogonal to as a d phi missing in the formula. So xi is orthogonal to the gradient of phi, and that means that its xi is lying in a hyperplane. And so the characteristic set in this situation is an n-2 sphere if you're in dimension n. Okay, so this is very important because of the non-self-adjoint character, you need to be careful. And also you cannot deal with elliptic operators. So meaning that it's difficult to invert this operator. So let me start with the first problem, which is the fact that the operator is non-self-adjoint. So it's known since the work of Hormander that for non-self-adjoint operators, there's a condition to have solvability of such estimates. So if you go back to the Kalman estimates, because it's non-self-adjoint, in certain situations, you can construct quasimodes, that is approximate solution of P phi u equals 0, in such a way that it contradicts the estimate. What is the condition? That was derived by Hormander, is that if you look at the real and the imaginary part of the principal symbol, the Poisson bracket must have a sign. It has to be positive on the characteristic set of the symbol. So whenever the principal symbol vanishes, you need to have a Poisson bracket which is positive. Okay? So that means that if your phase phi does not satisfy this condition, which I will refer to as subellipticity condition, the estimate cannot be true. So it's sometimes a problem to construct such a wave, but again, I will not be interested in that problem, just trying to speak about the estimates. So in the rest of the talk, I will be interested in specific Kalman weights, which are those for which the sign is actually strict. The Poisson bracket has to be strictly positive. Okay, and these, let's say, are the ones which are mostly used in control theory and in a lot of unique continuation problems. There are other weights which appeared, were introduced by Kenny Tröstrand and Ullmann to study the boundary elliptic inverse problem, that is Calderon problem with partial data. And this is a situation where the Poisson bracket is actually 0. So there's a sort of a commutation property of the real and the self-adjoint and the skew-adjoint part of the conjugated operator. Okay, and what I should say is, because I won't talk so much about that later on, when X and Y are, let's say, L2 spaces or Sobolev spaces based on L2, to prove such estimates, of course, one uses a lot the Hilbert nature of L2, that is scalar product. And the estimate are usually proved by commutator methods. And you can kind of guess that the condition on the Poisson bracket will give you some positivity of the commutator between the self-adjoint and the skew-adjoint parts of the conjugated operator. Has to be a little bit worked upon, but this is a classical correspondence between the Poisson bracket of the symbols of two operator and the commutator. So this is usually the kind of techniques which are used, very L2 techniques, which are used in the L2 case. This, of course, well, up to my knowledge, I don't know how to do that with Lebesgue spaces. Well, first of all, there's no scalar product, and it's difficult to do commutator estimates in that spirit. So now, what do I mean by global Kalman estimates? So I don't know exactly who coined out this term of global, but if you look at the first estimate I showed you, the function u was compactly supported. Usually, the compact can be chosen quite small. And in that sense, those are local estimates. And by global estimates, I mean estimates which also take into account the behavior when there's a manifold with boundary. So compared to the first one, I wrote an example, which is a Kalman estimate for the Laplacian on a compact Riemannian manifold with boundary. And what you see is that now you have the first one, which I wrote with x equals h1, y equals L2. And then there are two new terms, which are in red now, which are boundary terms. Okay, so here I have chosen to take test functions which satisfy a Dirichlet boundary condition. That is, they cancel on the boundary, but the normal derivative can be non-zero. And what you see is that I'm trying to control also with boundary terms. And boundary terms usually which are supported or localized only on one part of the boundary. Typically, the part of the boundary where the normal derivative of the phase of the weight of the Kalman weight has a sign, is positive. Okay, so this d plus of m is typically the part of the boundary where the normal derivative of phi is positive. This will come back later, of course, in which very nice. Okay, so those estimates are used, let me say, first, they are not needed usually in unique continuation problems, because those are local problems where you start proving that a solution is zero in a neighborhood of a point, and then you have like a peeling argument or a connectedness argument to go to the global unique continuation. But if you try to quantify, so have estimates to quantify unique continuation, those estimates are usually useful when you are dealing with PDEs on with boundary conditions. So I will be mainly interested with the Dirichlet boundary condition. They are also useful in control or stabilization problem. They were studied a lot by Lebeau and Robiano for the control of the heat operator and the stabilization of the wave equation with damping, and typically on open sets with boundary or on manifold with boundary. And also very useful in inverse problem with partial data, because if you look at the estimate I gave as an example, you see that you control gamma 1. Yeah, I should have said that gamma 1 is the value of the Dirichlet to Neumann map, is the normal derivative of u at the boundary. And what you can see is that typically those kind of estimates give you a control of the Dirichlet to Neumann map from one part of the boundary to the other part of the boundary. So of course, if you have partial data in inverse problems, that means that you have only information on one part of the boundary, and those global type of estimates might give you information on the other part. Okay, and this is actually why this notion of limiting Kalman weights was introduced in this study of the Calderon problem with partial data. Now the techniques, how do you go from usual Kalman estimates L2 to global ones? Well, either it's just because in your proof you're doing integration by parts and then boundary terms arise and you try to split them correctly on the right and left hand side of the estimates. But there are also pseudo-differential techniques which were very introduced and used quite systematically by Lebeau and Robiano, and which is the ones that we are also using with Rémy. I would say not so much about it, but you will see at the end that I'm talking a little bit about that. Okay, so now I've said what Kalman estimates were, global Kalman estimates. Now I'm speaking about Kalman estimates in Lebesgue spaces. So first of all, they were, people started to study them because they were interested in unique continuation properties of the Schrödinger operator, with an unbounded potential. So you assume that you are on the Euclidean space, M here can be the Euclidean space of dimension D, and you're looking at a potential which is in L D over 2. Why is this D over 2? Is because it's the sharp exponent for unique continuation. So there are known counterexamples now if you go below the regularity of LD over 2. Okay, so L2 Kalman estimates are enough to deal with unique continuation for the Schrödinger operator with L infinity coefficient. And then if you use probably Sobolev embedding, you can go a little bit below L infinity. But to go to LD over 2, Sobolev embedding and L2 Kahneman estimates are not enough. And this is the reason why Jerison and Koenig in the 80s proved Kahneman estimates in Lebesgue spaces, which are not obtained just by Sobolev embedding. Okay, they are and they are sharp in the sense that, again, because unique continuation is sharp for potential for D over 2, basically the exponents of the two Lebesgue spaces are more or less the best ones possible. I should say that the weight they used is a typical weight which is used in unique continuation, which is log of norm of X. And this is a limiting Kalman weight. So it's the situation where the Poisson bracket vanishes on the characteristics. But and then, well, maybe I will speak a little bit about that when I will do a short bibliography. But the case of the variable coefficients was studied by Sorge, and this is a study that we use a lot with Rémy to prove our estimates. So in some sense, we are interested in proving the analog of Sorge's estimate in the case where the manifold has a boundary. Okay, some remarks on LP Kalman estimates. The first one is that the two Lebesgue spaces are dual to each other. So if you do the computation, this is P and P prime where you have dual exponents. And also they are derived in the way that multiplication by potential in LD over 2 sends one into the other. And the last thing is that the dimension is bigger or equal to 3. You see that for D equals 2, you have L infinity spaces, and this is a quite different matter. Okay. So they are not true for D equal 2. The other stuff, which I have not really focused on in L2 Kalman estimates, is in L2 Kalman estimates, you're losing derivatives, and this loss is measured in powers of H. And this is due to the fact that this is a non-elliptic estimate, and you're losing half a derivative with respect to the Laplacian. For Lebesgue spaces, it is in some sense an elliptic estimate in the sense that you're not losing derivatives, provided that you're measuring derivatives in Lebesgue regularity terms. Okay, so as if you were doing Sobolev embedding. Okay, so if you were able to prove elliptic or L2 Kalman estimate without loss, you would get the LP estimate just by Sobolev embedding. Okay. But here somehow is exactly, and this is just a small computation which corresponds to Sobolev embedding. If you measure the difference between the two exponents is 2 over the dimension. And that means that somehow in Lebesgue currency, this is 2 derivatives which corresponds to the Laplacian. Another important remark is that the way that I have written it, the estimate cannot be perturbed a posteriori. That is bad news, because if you want to localize estimates, you need to use partition of unities and cutoff. And when you commute the operator with the cutoffs, this generates first order terms, which cannot be a posteriori absorbed into the estimate, at least to the Jerison and Koenig estimates. And this is a leitmotif in the theory of Lebesgue Kalman estimates. So you have to think a little bit how to deal with the remainder terms. Luckily, I will show you estimates which can be perturbed by first order terms. And then the last comment is that commutators are not available, or at least we don't know how to use them. And so the proof of Kalman estimate has to be replaced by construction of approximate inverses, that is parametrices. And this is what I will be doing here. So what is our goal? Is to prove global Kalman estimates in the case, in the LP case, in the variable coefficient case, so that is in a compact Riemannian manifold with boundary. And this will be done using actually the construction of Sog's parametrics and proving good boundedness properties. And to deal with the boundary term, use the pseudo-differential techniques designed by Lebeau and Robiano to study the boundary terms. Applications which are ongoing, for instance, we would be interested to get decay estimates for the semi-group wave operator with damping and with an unbounded potential, so in some Lebesgue space. Okay, so let me just give you the main results, and then I will speak a little bit about the proof, try to give you some hints of some, it's getting dark. So my setting is a compact Riemannian manifold of dimension higher than 3. This is because of the d minus 2 in the Lebesgue exponents. And I consider the Laplace-Beltrami operator on this manifold. And the important thing is to concentrate on the higher order or the principal term, which is the one where you have two derivatives and some metric with variable coefficients on in front. So again, I'm using the notation gamma 0 is the Dirichlet trace operator and gamma 1 is the Neumann trace operator. And I will suppose that we have a Dirichlet condition. So I'm not interested, or let's say it would be more difficult to try to get estimates in the case where the Dirichlet trace is non-zero. But that's an interesting problem also. And as usual, I denote the principal symbols of the Laplace-Beltrami by small p. So as I said, I insisted on that. The phase phi satisfies the subellipticity condition, and here means strict that the real and the imaginary part of the principal symbol of the conjugated operator is strictly positive on the characteristic set. We are interested also in the case where this could vanish, but it seems right now a little bit more technical. So you can actually compute, and there's a way of thinking of this as some kind of, I think there's a question maybe. Someone raised.
Yes, Daniel, you can unmute by yourself.
I think yes. The question is whether asking for a positive lower bound, is it too ambitious to ask instead of bigger than 0, bigger than epsilon? I mean, is it possible, or does it make sense?
Yeah, of course it makes sense, and in fact, in somehow it's how general limiting Kalman Kalman estimates in the case where it vanishes are proved, is by doing some kind of convexification which puts an epsilon there, and then you can sort of follow the dependence with epsilon. That is in the L2 case. In the LP case, we would be interested in doing something like that, but right now is not completely. But yeah, it's a very good question, because the case where this can actually be 0 is interesting, and so to go into that direction, putting a parameter which goes to 0, is a very. And this is also in the L2 case is usually what is used to absorb first order term also. So, but right now I'm just keeping to the simplest case.
Okay, thank you.
Okay, and as I said, the gamma plus and gamma minus are the set in the boundary where the normal derivative of the weight is positive, and actually you need to be a little bit more. You need to take a neighborhood, an open neighborhood, or neighborhood of this part. Okay. The part where this is 0 again is usually a little bit tiresome. And so this is the theorem. So as you can see, it looks like the example I gave you in the L2 case. You're controlling, so I'm using the convention that I put 1 bar for norms which are set on the boundary and 2 bars for the inside of the manifold. Okay, and so what I'm controlling is the LP norm by the LP prime norm of the Laplacian. And then I have a first order term here, which allows us to deal with perturbation, with a posteriori first order perturbation, essentially because the h minus 1 over d, when h is small, this is large, and you can absorb constants in that. So I should say that SOG's estimates are exactly those estimates without the boundary term, and with the manifold without boundary, let's say, or a function which is compactly supported and is flat on the boundary. I will forget in the rest of the talk of the first order term. Okay, so I will just deal with the main part, which is the LP prime estimate, and a little bit with the boundary. Okay. Okay, where is this? Oh, yeah. Okay, so let me just give very briefly give some references, and this is very short and incomplete because, of course, you can say a lot on. People have been working a lot on Kalman estimates for other operators, also for the wave operators. So here I'm just putting some references in the case of Lebesgue Kalman estimates, so LP Kalman estimates, and for elliptic operators. So as I said, this was started by Jerison and Koenig for the Euclidean Laplacian, and they proved strong and weak unicontinuation. There's a paper of Koenig, Ruiz, and Sorge where they are interested in linear Kalman estimates. And it's also a very interesting paper because it gives some relation with resolvent estimates for the flat Laplacian operator. Sorge was interested in unique, strong, and weak unicontinuation in the case of variable coefficients. And so we've been using a lot his article. So he will be, I will talk a lot about his results. And then later on, there are more sophisticated unique continuation problem. Tom Wolfe was interested in the case where you also add unbounded first order terms. And this is much more complicated because the Kalman estimates are complicated. Koch and Tataru upgraded Wolfe's results to the case of variable coefficients. And they gave also counterexamples to some of the unique continuation results for elliptic operators. I'm mentioning also some of our work with Koenig and Salo, where we were interested in LP Kalman estimates with limiting Kalman weights. And again, we relied a lot on the result of Koenig, Ruiz, and Sorge, and were interested in the relation with the resolvent estimates. And I'm also mentioning, there are several books on Kalman estimates, but I'm mentioning this is my PhD advisor, Nicolas Lerner. And there's a chapter on LP Kalman estimates, but the book is a lot on L2 Kalman estimates, and there's a very interesting reference on Kalman estimates. So on the side of global, this is a subject I know less also. So probably I'm mentioning results that I'm aware of, and that so the two first ones, they were not the first Kalman estimates with boundary terms, but they used this sort of differential and this systematic techniques to deal with boundary terms. Is this two papers on the heat, the control of the heat equation and the stabilization of the damped wave equation. I'm mentioning also, this is because I guess also of my interest, result of Le Rousseau and Robiano, where they are looking at situation where there's an interface, and there are two metrics on different side of the interface, and you try to prove L2 Kalman estimates with boundary terms, and because of the coefficients are jumping in the interface. And again, there's a very interesting book on Kalman estimates by Rousseau, Lebeau, and Robiano. These are 2 volumes just on elliptic Kalman estimate and just on L2 Kalman estimates, and in particular with boundary terms. Okay, so now let me talk a little bit about the techniques that are used to prove such estimates. And as I said, we rely a lot on the paper by Sog in the variable coefficient case. So the first thing is what I was saying is the conjugation. So you take V to be exponential phi u, and you see that the Kalman estimate is exactly the same as the one I have written here. There's no exponential weight now, but there's a conjugated operator which is non-self-adjoint and is semi-classical in the sense that you need to take care of the dependence with respect to the parameter h. And again, I will mainly deal with the LP prime term, not with the derivatives. But it's a good thing that they are here because all the localization arguments and techniques can be done because they generate first order errors which can be absorbed here, mainly, as I said, because there's this h minus 1 over d which is there, which is large when h is small and which allows you to deal with all constants. Okay, so I will forget about this term, but it's important because precisely of the errors. So this is what I say, because of this first order terms, you can localize, that means use a partition of unity and deal with functions which are now localized in small neighborhoods where you can take coordinates. So I'm writing things in coordinates, and from now I'm imagining that I'm on RD, okay? And what you can do is actually you can choose coordinates in such a way that the weight is equal to xd. Okay, so you're taking coordinates in such a way that the weight is xd, and in such a way that the principal symbol of your Laplacian is psi d to the square plus some metric, but which depends only in psi prime. So psi prime is all the d minus 1 first variables. Okay. And something I should have said also is that the estimates, of course, are sort of invariants by change by conformal change of the metric. So that means that you really can take 1 in front of xd to the square. Okay. And so with this computation, you can compute the principal symbol of the conjugated operator. And what you see is, as I said, is that there's a complex complex valued function. There's a real part and an imaginary part. The imaginary part is very easy. And you see that the characteristic set is xd equals to 0. So that's localizes in a hyperplane. And then g prime of c prime minus 1 equals 0. So that localizes in a sphere in the psi prime there. Okay. And now the subellipticity condition is just the Poisson bracket between the real and the imaginary part. Okay. So since the imaginary part is so simple, you can see that this is just the derivative minus the derivative of g prime with respect to xd. Okay. So the subellipticity condition in that setting tells you that somehow this function g is decreasing with respect to the xd variable. And that's very important. Of course, this is expected because with the wrong side, you know that the estimates cannot be true. Okay. Okay, so as a guideline, I just want to give a model where you can actually do computations. Okay, and this is the model. Is let's say you have some kind of Laplacian operator with variable coefficients, but the variable coefficients are very simple. It's 1 over 1 plus 2xd. And when you take the derivative, indeed, you see that this is strictly negative. Okay. And the last simplification I want to do, which is not, which is really a big abuse, is that I'm also assuming that somehow the boundary is given by xt equals 0. So that means that the phi function is the distance to the boundary. Of course, this is a very limiting example, but let's say as a first and for exposition, it's simpler not to have two different variables, one for the weight and one for the boundary. So think that phi, in certain situations, certain problem, you can use actually some construction of phase like that.
Sorry,
Okay.
I have a question.
Yeah.
With respect to the previous slide. So the last condition is the case if, for example, one has a small neighborhoods at the boundary. Yes.
Yeah.
Okay.
Yeah. That I should have said also. I'm taking coordinates close to the boundary. Okay. Inside is like SOG actually. For all neighborhoods which are in the interior of the manifold, you can almost you can do SOG's estimates, and you don't need the boundary term to. Okay. So it's really in a neighborhood of the boundary that you need to do the estimates. That you need to do something different. Yeah. Thank you for that question. So that was an observation made by SOG, is that, of course, in this situation, you can actually factor the conjugated operator, and there's a good part and a bad part. The good part is an elliptic factor. If you see the left factor, this never vanishes, okay, except maybe for psi equals 0, but so you have an elliptic factor, and then there's a bad term because this one takes care of the characteristic variety, okay? And this corresponds to a factorization of the conjugated operator where you have an elliptic pseudo-differential operator, and here some non-elliptic pseudo-differential operator. Why pseudo? Because you took the square root of a quadratic polynomial, so you end up, for instance, in our model with something which is pseudo-differential, okay? So I will forget about the E phi factor, the elliptic factor, because this is easy by Sobolev embedding to give you some of the results. You really need to concentrate on the bad factor, okay? And on the bad factor, because it's the square root of G prime, you have the same sign condition than for G prime. That's the subellipticity condition, okay? I'm not doing so good in terms of the. So, so you want to prove a parametrics. So you want to prove such an estimate. Let's forget to begin with the boundary term. So I'm in the situation of SOG. I want to prove an estimate like that. Well, it is enough to construct an approximate inverse, a left approximate inverse to P phi. And as I said, E phi I'm going to forget about. I'm going to think about the bad factor. Okay, so when I put this sign is to say that, of course, it's not an exact, but there are remainder terms, but they are lower orders, and they can be dealt with by the first order terms in the Kalman estimates. Okay, so if you have such a parametrics, the Kalman estimate is just showing that T phi is bounded, is a bounded operator from LP to LP prime, where P is 2D over D plus 2, okay? And as I said, I will forget about the elliptic factor. So constructing a left parametrics is easier to construct a right parametrics. You have to do it for the adjoint, and beware that this changes the sign in front of, instead of having plus I, you have minus I. This is because I'm looking at adjoints, okay? And the construction of SOG is to look of the parametrics using the construction typically done by Adamar, and that is you do almost like in the pseudo-differential case, you divide by the symbol, and then you have a phase which is not exactly linear, but satisfies an iconal equation. And the iconal equation is done in such a way that when you apply the operator on T phi star, the denominator cancel with the fact that the phase is solving the iconal equation. so that the singularities which might appear from dividing by this factor, which can be 0, disappear. Okay. Yes, I wrote, my notation is to write the kernel of the operators. This is why I'm writing x, y, and there's no. So I'm using the same letter to denote the operators and the kernel. Okay. So
sorry, just
yeah,
the,
sure.
the talk is very interesting to me. But then you wrote this kernel. This is the kernel of a Fourier integral operator, yes? Because
not really, because
not
you're
really?
dividing by something which might vanish. Okay, so your amplitude is non-smooth.
Okay, the amplitude is not. Okay.
Think that CD might come close to 0. So it's not exactly a Fourier integral operator, but you're right, it looks like a Fourier integral operator. And the other difference is that if you look at the iconal equation, this is a complex equation. So the phase psi is complex valued. So you have to think of it as a complex Fourier integral operator. So let me just write to you what happens in the model case. So remember, in this very simple case, you can actually explicitly compute the solution to the iconal equation. Okay, so there's an expression. It's not very interesting. What is interesting is you have a linear phase, like for a pseudo differential operator, and then you have this complex part, an imaginary part of the phase. As I said, this is due to the fact that you have an iconal equation. But this phi plus, if you compute and do a Taylor expansion, you see that it is positive. Okay, so that the exponential is decaying, which is a good thing. If not, of course and there's a 1/h missing also here. Sorry, in the phi plus, it should be divided by h. You have to think that psi, because of the characteristic set, psi is of the size of 1/h. Okay. Okay, and the fact that this is strictly positive is due to the subellipticity condition. Okay, without the subellipticity condition, this could be 0. What is in front here? Okay, so this is why it's very important. You see it at the level of Fourier integral operator or parametricis, is that the phase has to be an exponential which is bounded. Okay. Okay, so let me say that now. So this is the analysis done by Sog. There's nothing really new. We write the parametrics slightly differently, but this is his analysis. And then he proved, and you can do it in the same way, that this T phi has good continuity properties between your Lebesgue spaces. And this gives you Kalman estimates for terms which are supported inside the manifold. Okay. So now I want just to give some ideas how you perform the analysis at the boundary. Okay. So what I have neglected so far. This is already quite involved, but the boundary adds a little bit of involvement. So I'm the situation same situation. And the thing is, maybe this is something I should have said, is that the construction of the parametrics is without boundary condition. Okay, you don't try to do a parametrics which satisfy boundary condition. This is much more involved. For the wave equation, that is the Melrose-Justrand construction of such parametrices. But here we don't try to do this. We construct the parametrics on a neighborhood of the manifold. So you extend slightly the manifold, and you do the construction really in a neighborhood of the boundary. But you can see the effect of the boundary in the following way. So you take your function, and so I'm working again in coordinates in a small neighborhood of a point on the boundary, and I extend the function v by 0 in the other side of the. So the manifold M is xt positive, is the upper half space, and I extend by 0 brutally. And when you do that, when you apply the operator, of course, you have boundary terms which appear. Okay. So because you're assuming Dirichlet boundary condition, you just have the Neumann trace of V which comes in. Okay? And therefore, if you apply the parametrics which you have constructed, so to this identity, you see that you obtain T phi of the extension of F. So F you have to think is P phi of V. Yeah? It's the term that you want to have on the right-hand side of the Kalman estimate. And then you have an extra terms, which is not in SOG's analysis, which comes from the fact that you have extended brutally and that you have boundary terms. Okay, so you have an operator acting on the Neumann trace. And this is what you need to understand, is how this operator is bounded. Well, this is just the way I'm doing it, is you're right. And of course, the extension doesn't change the LP norm. So the first term, you just use the SOG's estimate to get what you want. And what remains to understand is what kind of estimate you can have on the operator acting on the Neumann trace. Okay, and this is what I wrote, is exactly this one. Okay, and this you can do at least in the very simplified model case I've presented, because there's an explicit computation of this boundary operator, and then you can apply more or less the techniques by SOG to prove that indeed you have such an estimate, that it sends. So it's sending an L2 on the boundary to, LP on the boundary to LP prime in the inside with some dependence in H. Okay, so you're halfway now. You're controlling, you have a Kalman estimate now because F is P phi of V, and you have a boundary term, but the boundary term is localized on the full boundary. Okay, so now you want to finish and say need additional control of the term. Yeah, so with the very simplifying model I've given, we're sort of done, because I've chosen a model where the phase, the Kalman weight, sorry, it should be a curly phi, is strictly positive on the whole boundary, so there are no other terms. But in the general case, of course, you have to deal with boundary terms which are not in this situation, where d nu phi is not strictly positive. Okay, so here you get out of the model case I gave you. And in that situation, you need to estimate the Neumann trace on the full boundary by the Neumann trace on this gamma plus. Okay, and with an additional term, which is always the source term of your equation. Okay, so this is what you need to do. And I'm almost over, but that's okay, because I don't want to say too much about it. So because here it gets a little bit more complicated. You cannot choose xd to be both the coordinate of the boundary and the Kalman weight. So what you choose is to keep xd as the normal, the geodesic normal coordinates. But then the phase phi, of course, depends on other variables, and you see that your conjugated operator is a little bit more complicated. Okay. Nevertheless, you can still factor out into a product of two operators. So it's not as before. There's not a bad and a good one. It's more complicated. So rho and plus and rho minus are the complex roots of this polynomial with respect to xd. And the last part, which is using the techniques derived by Lebeau and Robiano, is a careful analysis of where the roots are located in the complex plane. Okay, so for this, you need to do really micro-local analysis. You need to localize in the phase space according to the place where the complex roots are located in the complex plane. The good news is that this is just the estimates somehow that you want to obtain are estimates on the L2D over D plus 2 space. And that means that there's no Fourier integral operators involved somehow. So it's just pseudo-differential analysis. And that's good news because, of course, the continuity of such operators is much easier. Let me just give you a hint of why you need to localize according to the location of those two complex roots. If you think about the situation of ordinary differential equation, you take a second order ordinary differential equation with constant coefficients, okay? And you solve. There are two, and the way you solve is just you compute the roots of the characteristic equation. This gives you two complex roots, and the solutions are exponential of those complex roots. And of course, they have exponential behavior depending on the sign of the real part, let's say, of the complex roots, okay? Now, the question is, in this situation, how many boundary conditions do you need to solve your ODE? And you need to think that the analog of our situation is you want to solve with solutions which remain in some L2 space. So you don't want to have exponential behavior at infinity. So what you see is that if the real part of the two complex roots are positive, this cannot happen because you have exponential behavior at infinity and somehow it's not L2. If the complex roots have one real part which is positive and one real part which is negative, then you can disregard the solution which is exponentially growing. So that means that you just need one boundary condition to determine the decaying exponential. And then there's the situation where the two real parts are negative, then both are exponentially decaying and are genuine L2 solutions. But then you need two boundary conditions to determine each of the exponential. Okay, so there's a situation where you just need one boundary condition, and this is somehow the center point of this Lebeau and Robiano analysis, and actually also it goes back to Calderon analysis, where you can really look at the number of boundary conditions that are needed to control. Okay, and this is somehow what you do here. So you need to do microlocal analysis to micro-localize near sets where rho plus and rho minus have the correct behavior. But as I said, this is more pseudo-differential calculus, and this is easier to get LP bounds in this calculus. And I'm sorry, I think I was a little too long. Thank you very much for your attention.
Okay, thank you very much, David, for very nice, interesting talk. So maybe if someone has some question.
Maybe I have a question, maybe a small question about the nature of the operator, because the Laplacian is a local operator, yes? And this works well for local operators. I wonder if you know something for non-local operators, let's say for fractional.
Oh, okay. So that's we've been discussing this question with Julio. So for the fractional Laplacian, yes, there are results of Ancana Ruland, where she looks at unique continuation properties, and I think with unbounded coefficients. So there's a series of papers where she looks at the case of the fractional Laplacian. And in this situation, there's a sort of trick, which is if you look at for example, if you look at the square root of the Laplacian, you can look at it as a Dirichlet to Neumann map if you extend variables. Okay, so this is a trick which has been derived and introduced by Caffarelli and Sylvester, I think. I'm not sure, but and so somehow there's a way of understanding this non-local situation as a situation where you have an extended, you have an additional variable.
Thank you very much.
Is there any other question? I have, well, in the meantime, maybe I have one. Are there some known consequences, maybe even in the without boundary case, for the understanding of the eigenvalues?
So actually, the paper of Jerison and Koenig is applied to show that there is no positive eigenvalues, no embedded positive eigenvalues for the Laplacian plus potential. So there's they are used in spectral theory.
And in the case with boundary, in this case where you are discussing LP boundary and so on, it's also the same.
Okay, so that I know a little less, but let me tell you some application which is also there are some estimates of I think the first people who derived them were Jerison and Lebeau, and they also were studied by Lebeau and Zuasua and Robiano and Lebeau and Robiano. And these are spectral estimates where you try to control you try to control some spectral function. So you sum the you look at a spectral projector where you you look at the spectral projector and you try to understand how you can control this by some it's like an observability type of estimate. So you look at a spectral projector on a small open set, and what you try to understand is the dependence with respect to the spectral parameter, which is exponential. And this also makes sense on a manifold with boundary. And one way to prove that is again to extend the Laplace operator by one variable, and then perform Kalman estimate on the extended operator. So here again, in the manifold case, well, I think there are estimates in this situation.
Okay, thank you, David. Maybe.
Okay, thank you very much.
Thank
If
you
you have more
very
questions.
much.
No more questions. So let's thank to Professor Julio Delgado and Professor David Dos Santos for this amazing talk. So now we are on time to hear our next speaker.
Should I stop the? Yeah. Okay.
Yes. Thank you, Professor. So now we can hear our next speaker, Professor Del Pino. Professor Del Pino, can activate your camera?
Yes. Just a second.
Okay, so maybe we will say some words in Spanish and in English to present you, Professor, and then you can
Should I share the screen? Or
yes, please, you can share your screen.
Let me see. Okay.
Okay.
So well. Go ahead, Milton.
Buenas tardes a todos los que nos acompañaron este día. Hoy tengo el honor de presentar al destacado profesor Manuel Del Pino, quien actualmente trabaja como docente e investigador en la Universidad de Bath, en Inglaterra.
Good afternoon to all of you. Good afternoon to all of you who are with us on this day. Today, I have the honor to introduce the outstanding Professor Manuel Del Pino, who currently works as a professor and researcher at the Bath University in England.
El profesor Del Pino es ingeniero civil matemático por la Universidad de Chile y doctor en matemáticas por la Universidad de Minnesota en Estados Unidos, título que recibió en 1992 y que le dio la oportunidad de tener una membresía postdoctoral en el Instituto de Estudios Avanzados de Princeton y más tarde liderar la prestigiosa cátedra Dixon en la Universidad de Chicago. Desde 2009 es miembro correspondiente de la Academia Chilena de Ciencias.
Professor Del Pino is a mathematical civil engineer from the University of Chile and a PhD in mathematics from the University of Minnesota in the United States. A degree he received in 1992, which gave him the opportunity to have a postdoctoral fellowship at the Institute for Advanced Studies from Princeton, and later led the prestigious Dixon Chair at the University of Chicago. Since 2009, he has been a corresponding member of the Chilean Academy of Science.
Entre sus temas de interés se encuentra el análisis de ecuaciones diferenciales parciales no lineales, una área central de la matemática y su integración con otras ciencias. Por sus aportes a las matemáticas, fue galardonado con el Premio Nacional de Ciencias Exactas en Chile 2013. Y hoy tenemos la oportunidad de presentarlo como uno de nuestros conferencistas en el ICMAM 2022. Adelante, profesor Del Pino.
Among his topics of interest are the analysis of nonlinear partial differential equations, a central idea of mathematics, and his interaction with other sciences. For his contribution to mathematics, he was awarded the National Prize for Exact Science in Chile 2015, and today we have the opportunity to present him as one of our speakers at ICMAM 2022. Professor Del Pino, you can continue with your talk.
Ok. Bueno, parto por agradecerles la introducción, Duval Milton, muy generosa, gracias. Y muchas gracias a los organizadores por la invitación. So thank you very much to the organizers for this invitation. It's an honor for me to participate in this great conference. Okay, so I will start now. So the topic of my talk today is a classical topic in fluid dynamics, which is the analysis of solutions to the incompressible Euler equations with the highly concentrated vorticities. Okay, so the subject is this equation, which is the classical Euler equation in the entire space, where by n I mean 2 or 3. Okay, and this is a transport equation where this term appears as a sort of Lagrange multiplier because of this constraint, of the incompressibility constraint. And vorticity, by definition, is the curl of u, so it's a measure of how the velocity field of the fluid tends to rotate, okay, around an axis. And
Profesor, disculpe.
Sí.
Parece que hay un eco extraño. ¿Hay dos dispositivos cerca suyo?
Sí, espera, puede ser que... Espera, voy a cortar este mejor. ¿Ahora?
No.
¿Qué tal ahora?
No, señor. Quizá...
¿No me escucha?
If someone has activated the microphone, please unmute the microphone because there is some interference. Perdón, profesor. Es que se escucha un eco.
Puede que esté muy fuerte. Puede que esté... Espera, si quieres me pongo los audífonos. A ver.
Disculpe.
¿Ahora?
Profesor, excelente. Muchas gracias.
Ya, muy bien.
Okay, thank you, professor.
Ok. Un segundito que voy a partir el video.
Muy bien, perdón. Gracias.
Ups. No me lo agarra el video. Bueno, en fin, no importa. Ya, a ver. Well, okay, so I continue then with the presentation. So this is these are the Euler equations for an incompressible fluid without viscosity, okay? And U represents the velocity field and vorticity is given by the curl of U, which is this quantity. And now then for a solution of the solution in 2 dimensions, okay, the velocity field has 2 components, U1 and U2. They are a function of just 2 space variables. And in that case, the curl of U, which is the vorticity, can be identified with the scalar function, okay, which is precisely this quantity here. And the nice thing of this quantity is that it satisfies an equation with a similar flavor as the Euler for the fluid, except that it is not vector valued and it doesn't have this this gradient of the pressure term. Okay, so this is a simple transport equation. Okay, so it's the vorticity is transported by the velocity field, and besides, the velocity field can be recovered from this scalar omega by simply the following rule, okay, that I explained. Say the divergence zero condition for U implies the existence of a potential for U, in the sense that the perpendicular gradient of psi, where perpendicular means this notation down here, is equal to the velocity field. So psi is called the string function of U, and another nice thing is that if you compute simply the Laplacian or the negative Laplacian of the string function, you recover with that omega. Okay. Now, concerning this equation, the standard solution that we can choose is the Newtonian potential. The Newtonian potential is just the convolution with the fundamental solution. So when I write this equation in what follows, I will always mean this expression here, okay? The convolution of the fundamental solution with omega itself. Well, then you can see what happens. The U can actually be recovered from the velocity from the string function just by taking gradient pair of psi. Yeah. So in other words, the vorticity string formulation, which turns out to be equivalent to the original problem, okay, is given by this transport equation, this non-local transport equation, where the transport term is the gradient of the inverse Laplacian of omega itself. So this term is quadratic in omega. So this is why it is a non-linear, non-local equation. Yeah. And again, the inverse Laplacian of f will always mean this. And the velocity field can be recovered, as I just said, as the perpendicular gradient of this quantity, which is directly, you see, is given by this formula. This formula is what is called in entire space the Biot-Savart law. Yeah. And I remind you, the vorticity is precisely the curl of the velocity field. Okay. So concerning this theory for well-posedness of the for the Euler system in vorticity form. Actually, this has been well developed in 2 dimensions. So there are many results of this type. The classical one is due to Bolivner in the 1930s, Judovich in the early 1960s with his famous theory about well-posedness with initial condition in L infinity. Okay, so what that theory essentially states is that if you start with a bounded initial condition, yeah, maybe bounded and at the same time integrable, then you will have a unique solution defined in a weak sense for this problem, okay? And that solution is not just defined for a finite time, but it is defined at all times. As a matter of fact, if the initial condition, in addition to being bounded, is smooth, actually the solution cannot develop singularities in a finite time. So the solution is regular at all times. Yeah. So this is the classical theory for the Euler equation in 2D. Let me make a couple of observations. So concerning steady states, if we start with a solution of a semi-linear elliptic equation of this form, yeah, then it turns out that the pair psi omega, where omega is f of psi, so the right-hand side of this equation, corresponds to steady state of the equation V. Why is that? Well, the reason is that since if omega is f of psi of x, right? If you compute the gradient, you will get f prime times gradient of psi. Gradient of psi is always perpendicular to the gradient perp of psi, of course, so this is 0. And since there is no time dependence, this is 0 as well, so we have a steady state, okay, for the Euler equation. One example that I will refer often, right, is the of a semi-linear equation of this form is the Liouville equation. So, yeah, the Liouville equation is another classical object in mathematics. So in entire R2, the regular solutions with finite mass, as a matter of fact, are all known, and they are very simple. They are just given by this function, yeah, by this function here, which is called the Kaufman's-Cooley vortex. Okay. And well, it is not only this, but also translations and scaling, mass preserving scalings. So all the mass, all those guys corresponds to solutions of the equation. Okay, what would I like to do? I would like to describe the evolution of solutions to the Euler system, to the Euler equations, which have vorticities concentrated around a finite number of points. Yeah, this is my purpose. What does that mean? Okay, say imagine like this picture, which is of course a fantasy. Okay, I don't think this corresponds to any true meteorological situation, but say you have 3 vortices, okay, atmospheric vortices, so cyclones, typhoons, or something like that, okay, one after the other, just like in this picture. Of course, we don't expect that the 2D Euler be a good model, okay, for that, but necessarily a good model, but just to fix ideas. Okay, I am interested in situations in which this tendency to rotate is very concentrated around a single point. More precisely, I would like to idealize omega as having the approximate form, a linear combination of Dirac deltas. Why is this form reasonable? This form is reasonable in part, okay, because this the equation, as we can easily see, preserves mass. Yeah, it preserves mass also locally. Yeah? Then, since this is mass preserving, then if you start with a Dirac delta, you will continue seeing a Dirac delta. Essentially, you should continue seeing a Dirac delta. So the Dirac delta doesn't open up or regularizes in finite time. And these quantities here are constant. I call them 8 pi k kappa j just as a cosmetics, okay? But these are arbitrary constants. But the corresponding string function then corresponds to the corresponding linear combination of fundamental solutions. So like this. Okay, so now I will make I will go to what I would like to prove. So what I would like to do, I would like to analyze solutions with highly concentrated vorticities in a precise way, an analytically precise way. Well, this is a mathematical subject with a very long history. As a matter of fact, it traces back to the very origins of the fluid mechanics, okay? In particular, after the works by Helmholtz and Kirchhoff, and other works of many other people. Here I just mentioned some names. Yeah. And then let me explain you more or less in a language we would use today what they derived. What they were able to find was the law of motion of the center of the vortices. Yeah, because they should evolve in time. And this idealized quantity, which is not a function, okay, this is a distribution, then I would like to find a solution with this particular form, and I will show you what the centers should satisfy. Okay. Since the corresponding, let me call it omega s, okay, and the corresponding psi s, the string function, should be the corresponding linear combination of the fundamental solutions with poles at this center psi j of t, which I will find. Formally, we compute that the Euler operator, yeah, the operator for the Euler equation becomes this quantity here. So the differentiation in time involves gradient of Dirac delta times the derivative in time of the point, while these two terms, each of them is a summation, so you get a double summation like here, okay? Of course, you can see something a little bit ugly here, which is this, which is that for I equal to j, this quantity is singular, yeah, is singular, and we are multiplying it by a distribution, right, which is very singular as well, right? It's the gradient of a Dirac delta. So can we make sense of this quantity when I equals to j? Luckily, yes. And the reason is that gamma, okay, is a radial function of the argument x minus psi j, and the Dirac delta, in a sense, is also radially symmetric because it is invariant under rotations. Then in any reasonable sense of approximations or whatever, we can assume this. Why? Because if you compute the gradient of a radial function and multiply by the gradient perpendicular of another radial function, that product is automatically zero, okay? So this is true if delta was a function, just as gamma. So in the distributional sense, we can assume this, okay? This is a formal consideration, but reasonable. So we will have then that the omega s psi s will be a solution of the problem of the Euler equation. So this equal to 0, if and only if these coefficients are equal to 0. Zero where? Well, exactly at the support, right, of this quantity, which is x equals psi j. Yeah. And and that gives me K or capital N relations, and those relations read exactly like this. So this is a system of ODEs, which is an n-body problem, as you can see down here. Okay, so this system I will call K from now on, is because of Kirchhoff. And then here is the natural question. This is if you have a solution of this n-body problem do they represent true solutions of Euler, true regular solutions of Euler, which is what we will see in what we should see in reality, in physical reality. And this is a long-standing question that I would like to which I would like to give a precise answer. Okay. Okay. So to state the answer that I would like to give. Yeah. Let me consider the following regularizations of the Dirac delta and of the corresponding fundamental solutions. Yeah, I use Kaufman-Scully vortices to regularize the Dirac delta. How? Well, this W0 is the Kaufman-Scully vortex. This is a rather rapidly decreasing function, right? And then what I consider as an approximation of the Dirac delta is simply this scaling. So I divide the argument by epsilon, and I put here 1 over epsilon squared. So this is a bell shape, very concentrated around the point psi j if epsilon is small, right? And what are the corresponding string functions, or approximate string functions, I should say? It is precisely this. This is nice because this desingularizes the fundamental solution just by adding epsilon squared to this singular object. Okay, so it is a very simple regularization of the Dirac delta and of the string function. What is the statement that I would like to prove? I would like to prove that there exists an actual solution, a true solution, which looks approximately like this pair. Yeah? A true solution. This is not trivial because the points psi j are interacting. If you let psi j to be a constant and just one of them, then you will have a steady state automatically. Okay, but this is not the case in general. So let me observe, by the way, that the inverse Laplacian of this omega 0 of epsilon is precisely psi 0 of epsilon. This is the bottom line. And I recall the integral of omega 0 is a pi. Therefore, as you let epsilon go to 0, this epsilon regularization of the Dirac delta goes to the Dirac delta in the distributional sense, just like as I am showing here. Yeah. Moreover, actually, you also have a convergence of the kinetic energy density. The kinetic energy density is this quantity, right? This is the square of the norm of the velocity. And if you normalize it with this factor log epsilon, then you arrive to this this limit as when epsilon goes to 0. Okay, here is our result. Our result is that if we have a solution of the Kirchhoff system, Kirchhoff-Roche system, system K, which is this one, okay? And if we consider a solution which doesn't have collisions in a given interval of time, then the statement is that there exists a solution of the Euler system which differs little from this approximator psi 0 epsilon omega 0 epsilon. So it will be a regular solution that looks like this. Yeah. Okay, so this is a result I found in collaboration with Juan Davila, Monica Musso, and Junqing Wei. It was published a couple of years ago. And what we proved was the following then. Given a collisionless solution of the system K, there exists a solution of the problem V of the vorticity form for the Euler equation, which has the following form. It has this approximator of the linear combination of Dirac deltas plus a remainder, okay? And similarly for the string function. So here you have a remainder. In this remainder, the Laplacian of psi is going to be phi. Yeah, then, let's say this is the connection between these two guys, right? Okay, and the interesting thing is what we can say about the remainders. Let's start with the remainder of the string function. This remainder is in reality extremely small. Okay, its size is epsilon squared. It's of order epsilon squared. Look, this is essentially negligible compared with the main term, because the main term is very big, right? We have log of epsilon. Yeah, so it's a quantity that goes to infinity with epsilon. This quantity goes to 0 with epsilon. Okay, we have a conclusion a little bit more modest, okay, for the vorticity. The vorticity loses 2 epsilons, but we can still say, in reality, we can do much better than this estimate. But what you will see, anyway, let me put it this way. The string function has size epsilon squared. The derivative of the string function loses 1 epsilon, okay, because this will only be size epsilon. So the phi is 2 derivatives of psi. So this should be capital O of 1. As a matter of fact, you can get up to there locally, okay? But if you want a global estimate, this expression is better. Okay, so in particular, we have the weak convergence, the distributional convergence of the vorticity to the limiting singular quantity, and same for the velocity, for the kinetic energy. Okay, so now, if I can say a couple of words without going into details, for the construction of these solutions, this construction is quite delicate. I should mention that there is a prior result along these lines by Marchioro and Pulvirenti. As a matter of fact, 2 papers, one in 83 and a more recent dealing with a situation closer to this one in 93. They were able to capture the law of motion, yeah, last as here, but without any good information on the behavior at the critical places, okay, which is the behavior near the vortices. So the method is of a completely different nature. We use singular perturbations and precise approximations. Yeah, this is why we also need to work quite a bit more. So the ingredients go like this. We need to find an improvement of the approximation in powers of epsilon using elliptic and transport equations. Then after obtaining this good approximation, we set up the problem as a coupled system of inner problems near the singularities and an outer problem that sees the whole picture, which we call the outer problem. Okay. This scheme we call the inner outer gluing scheme, and we have used it already in a number of problems, some of them classical, as a matter of fact, with my collaborators. But those problems are more of elliptic and parabolic character. So and now we have seen that it is also a good tool for this particular question in Euler equations. Yeah. The improvement of the approximation is used combining elliptic and transport equations, which is natural, okay, because that's precisely the character of the Euler equation itself. And at the end, we find a priori estimates that allow us to solve the full problem, the full nonlinear problem, by a continuation degree argument. Okay, so let me go into some extensions of this result. One extension that has a look kind of similar, but is much more delicate, corresponds to the surface quasi-geostrophic equation. It has the same look, this equation, as Euler, except that here, rather than negative Laplacian inverse, okay, we have negative Laplacian fractional between S is a number between 0 and 1. And here the definition of this naturally, okay, involves the fundamental solution of the fractional Laplacian, which is this guy. Yeah. So the question could be the same. Can we find solutions with vorticities or whatever we call omega? But it's not vorticity interpretation, but doesn't matter. And the corresponding limiting system, if you do the same, if you play the same game that I showed you at the beginning, you get this system of embodied problem, KS. Yeah, this one, precisely this one. So with my former postdoc, Antonio Fernandez, who is now in Madrid, we have found the following result. If S is sufficiently close to 1, we cannot, unfortunately, we cannot go all the way with this below, but at least if S is bigger than this precise number, 0.937, okay, then it turns out that, again, for the collisionless solutions of this KS system, there exists a solution of the surface quasi-geostrophic generalized equation such that the corresponding solution, okay, omega, behaves like this. Now U0 is this quantity, which we may call a Kaufman-Cooley vortex generalized. These are actually connected with Sobolev embedding, Sobolev fractional embedding. These are the corresponding Talenti solitons, if you wish, okay, in the fractional case. Okay, a previous case, but actually in a situation valid for all S positive, was found by us, by collaboration with Davila Muson Wei and with Wei Yao from China, from Wuhan. We found a traveling wave solution in the form of a vortex pair traveling at a constant speed. And for the full problem, there were also partial results, okay? A very important thing is that the problem is more difficult, and it's more difficult for many reasons. One of them is that there is no Udovich theory. As a matter of fact, until today, it is not known if the solutions blow up in finite time. For the SQG problem, if you start with something regular, it is just not known, okay? It is perhaps expected. No, it's not clear. Huh? So we had to construct the solution by hand, and we had to overcome that particular difficulty, okay? With a similar scheme, but technically much more involved. And technically, we couldn't go below this specific number. Okay, let me say some words about the three-dimensional case, which is in fact more interesting. The three-dimensional and so far quite unknown. Okay, the three-dimensional case, I mean now solutions of the Euler equation, which are velocity fields, but with vorticity concentrated around a line rather than points. Yeah, in 3D that corresponds to lines. Here is an example. Okay, a tornado. Another could be smoke rings thrown by volcanoes. This is a phenomenon that happens. You can find nice pictures, okay, in internet about this type of phenomenon. This is a volcano Stromboli in Italy. And also, in addition, well, I have never seen this. Perhaps you might. So dolphins also do rings with water like this, yeah, using vibration, some form of vibration. Okay, so you may wonder, so what is the connection? What is the analog of this embodied problem, but now concerning the evolution of the curve in time? And that question was already considered by many people more than a century ago, and that gave rise to what is called today the vortex filament conjecture. So a very important contribution was made by Darrios. Darrios was a student of Levi-Civita, yeah, and in the early 20th century, he discovered the formal law of motion. Let me explain you that formal law of motion. The Euler equation extreme vorticity formulation is this guy here, yeah, and now it's more complicated. Of course, it is vector valued also. Okay, the velocity is the curl of the stream function, and the stream function is now a vector, which is this one. Okay. Now, what we want to find are solutions with vorticities concentrated on a time evolving curve, which we will call filament, which let me assume that it is parameterized by arc length. Okay, this is parameterization by arc length of this curve gamma of t. Yeah, in R3. So what the concentration statement in this case would correspond to a solution such that as epsilon goes to 0 looks like a Dirac delta uniformly distributed. This is in agreement with the computational laws, okay, of the Euler equation in 3D. What you will see, it is reasonable to look for, is a solution that looks like a Dirac delta, but along the tangent vector to the curve. This is what we would like to find. Okay. In reality, you cannot find it exactly like this as t goes to 0. However, if you make a scaling in time, and this is what the Rios discovered, yeah, and that change in time scale is this one here, then it turns out that you can find an asymptotic law for gamma of S when t is changed into tau, okay, into this scaling. Yeah. What is epsilon? Epsilon is the width of a tube that you take around the curve. Yeah. So this is it's the same role as epsilon in the two-dimensional case, but now think of it as a tube. Then the asymptotic law for the curve is this one. This is a dispersive equation, actually, for curves, which is the analog to the so-called curve shortening flow, except that the curve shortening flow, which is parabolic, what you have here is the normal vector to the curve. In this case, what you have is the binormal vector. This is what makes it dispersive. As a matter of fact, there are conservation laws. This flow, for instance, preserves length. Yeah, is one characteristic. And the binormal flow, as well as everybody knows, we have precise definition by Frenet formulas. Yeah. Okay. Then the vortex filament conjecture now is the following. Is a similar question. So, given a solution of the binormal flow of curves, gamma of tau, can we find a solution such that if I scale time in this way, I can obtain this convergence as epsilon goes to 0? That's the question. Okay, so I could try to do that by doing a regularization using, again, the Kaufman-Scully vortex for the Dirac delta. And in fact, that's a reasonable question. However, hard. It's a difficult question. Yeah, and we don't know how to answer it in full generality. And it turns out that we have been able to find only in some special curves. One that is completely, the two of them are classical, but a true proof only existed until recently, only in one case, which was the so-called vortex rings. Yeah, for Euler. This was first found by Frankel, and recently also the case of a helix had been considered. So these two guys, if you consider the centers, okay, the curves, a circle traveling with constant speed along its axis is a solution of the binormal flow. If you make the exact relations between radius and speed. And it is also the case for a helix when it rotates with constant speed. Okay, these two are classical solutions of the binormal flow of curves. So what we have been able to find are in the axisymmetric Euler-Noswirth case, which means this change of variables here. Yeah, we can find we can express the problem for the vortex ring as that of finding a solution of this equation, yeah, which is very concentrated around certain radius. The Frankel exact traveling ring solutions is a thin ring, like in the previous image, and traveling with finite speed. Those correspond to solutions to a PDE, which is of elliptic type, which is this one here. This I call Laplacian 5. No? And you can find solutions of this problem with different methods, variational, or degree theory or singular perturbations, whatever. And finally, you can get a solution corresponding to a vortex ring. What we discovered was that using the helicoidal symmetry, we can try a solution of this particular form. Yeah, very special solution, which is one concentrated around a helix. In that case, if you do the right computations, this is not a triviality, but the symmetries, the helicoidal symmetry was already known. If you write the corresponding equation, time dependent or tau dependent, you get this one for this matrix here. And what we look for are rotating helicoidal solutions, yeah, which are solutions generated with this symmetry. And you arrive at an elliptic problem. The elliptic problem is given by this, yeah. And well, this is a paper with Davila Musonway, recently appeared. We are able to find a solution of the equation when the nonlinearity, we take it again to be Liouville, okay? And in the limit, what we will see is the curve gamma, the solution around this curve gamma here, which is a helix corresponding precisely to the corresponding solution of the binormal flow, okay? Okay, so to conclude, let me mention the following situation in which we have found a very interesting progress, which is that of multiple vortex rings. How do they interact? Yeah, vortex rings are solutions, like as I show here. Yeah, traveling with constant speed to the right. But you can think of two rings that you let them interact. Yeah, in the axisymmetric Knox-Wheel case. And it turns out that already Helmholtz in 1858 formulated the question of what happens with such a motion. And what he conjectured was that, well, conjecture in the current mathematical language, that it happens what is shown in this picture. So the radii of each of the two rings, yeah, varies with time. And as the radius decreases, the velocity increases. So one of the rings penetrates the other, yeah, like in this picture. And then the green ring will do the same, okay? Reduces radius, penetrates, crosses the red one, and then successively, okay? This type of motion is called leapfrogging. And you can find a lot of literature about it and numerical simulations, even physical experiments with this. And the leapfrogging motion was already justified mathematically in the Gross-Pitayevsky equation by Gerard and Smets, but that's a completely different problem with other difficulties. What we found, and this is already a paper that you can find in arXiv, is the following. If you consider a solution to this law of motion, which is the analog of the n-body problem, but for this particular situation, then you can find a solution reflecting precisely the behavior of this, like this, two vortex rings crossing one to each other, and at distance, relative distance small, okay, 1/square root of log of epsilon. Just to, if you want to figure out the case of two rings, actually you can, if you let one point equal to minus the other, yeah, then you arrive to a system, to a nice Hamiltonian system whose trajectories are like this. So the bottom line is you start with an initial condition here and you get a periodic solution. Yeah, this is a nice characteristic of this problem, okay, of this particular problem. And every solution of this two-body problem is going to correspond to a periodic trajectory here. Okay, so and we are able to find a solution with precisely these scalings. Yeah, so this conjecture by Helmholtz can be answered with our techniques. However, probably previous techniques in the literature were not fine enough to detect this this phenomena. Okay, thank you very much for your attention.
Thank you very much for this presentation. Someone has a question for our speaker. We only have time for one question.
Yes, Professor, I have
Yes.
a question. Is there some reason to consider the first analysis only for dimension 2, dimension equal to 2? Is there any something explodes in this case?
Okay, in the two-dimensional case, it is of course easier, and it is easier because the concentration of vorticity only happens at isolated points. Yeah. So, and this is the type of solutions that we find. It is technically simpler for many reasons, and this is the reason why, for instance, in 2D, it is well known that the Euler system doesn't develop singularities in finite time. So a big problem, in fact, is in 3D, whether such things exist. It is not known. Yeah, and in 3D is a completely different thing, because now the object that evolves is a curve, if you want concentrated vorticities. And even though you can find the formal law, this was found more than a century ago, finding a true solution doing that is still completely open. We don't know how to do it, because what we have discovered is that you can do computations very fine, in which you can improve the approximations. However, finding a true solution by linearizing is not so easy, because you have a lot of instabilities arising is in the way for different values of epsilon. And this is something we have to be extremely careful with. We hope to have an advance rather soon, but it is not for us clear yet how to solve the full problem.
Thank you, Professor.
Thank you.
Okay, so thank you very much, Professor Del Pino, for this very interesting talk, very inspiring. Sorry, maybe we don't have more time for questions. Now we have with us our next speaker, Professor Christine Lauter. So let us, okay, let us see, Professor Lauter. I will give you the permissions. Okay, you can share your screen now.
Let me just check if can you hear me?
Yes, we can hear you well. Thank you very much for accepting our invitation.
Happy to be here.
Thank you. So we will say some words in Spanish and in English to introduce you to the participants. On the meantime, you can share your screen.
Let's see if this works.
Oh, well.
Okay. Good day,
Yes.
Professor. I will allow myself speak the next discourse in Spanish, but it will be translated into English. Okay. 1 second. Okay. En palabras de la profesora Alicia Dickenstein, lo que sigue es una breve descripción de la carrera matemática de alguien a quien considera wait. Wait, 1 second.
No soy Alicia.
Sí.
Yeah. Yeah, 1 second.
Is that Professor Alicia Dickenstein sent all some words for you? And then Cari is explaining this in Spanish.
Okay. You can start.
In the words of Professor Alicia Dickenstein, the following is a brief description of the mathematical career of someone that she considered his close friend and someone who she really admired so much. After graduating from the University of Chicago, Christine Lauter was an assistant professor of mathematics at the University of Michigan and then continued her research activities in industry. She worked at Microsoft Research during 22 years, where she was the head of the cryptography group and is currently a researcher at Meta, where she is the West Coast Director of Research Science at FAIR. She's a co-founder of the Successful Women in Numbers Network, a research collaboration community for women in number theory, and she has been the president of the Association for Women in Mathematics from 2015 until 2017. She's a fellow of the American Mathematical Society, the Society for Industrial and Applied Mathematics, and the American Association for the Advancement of Science in the section of mathematics. The lecture of Professor Christine Lauter will be on artificial intelligence and cryptography. She will explain to us how to hide our secrets from intelligence artificial and post-quantum world. So Professor Lauter, thank you very much. Please start your presentation.
Great, thank you. Muchas gracias. Mucho gusto estar aquí. No entiendo todo en español, pero si hay preguntas también puedo tratar de responder en español, en castellano. Okay, but for my talk, I'm going to give it in English. So thank you so much for inviting me. Thank you to Alicia also for those kind words. I'm very excited about this conference, and I hope to reach a wide audience in Latin America. I actually serve on the steering committee for Latin Crypt, which is a cryptography conference in Latin America. So if anyone is interested in connecting up with Latin Crypt, please let me know. So today I'm going to speak on artificial intelligence and cryptography, data privacy and security in the AI era. So this is actually a challenging task to do in a short talk. I would like to kind of give you an idea and an overview of two whole fields, AI and cryptography, and explain how they relate to each other in a complicated way. So as I said, not easy to do in 40 minutes, but let me try my best. And this is also an abbreviated version of my block community prize lecture from July at the ICMAM annual meeting. ICMAM is the Society for Industrial and Applied Mathematics. And so I'm just trying to give a kind of a shorter version of that talk here. So first, let me explain what I mean by the AI era, or AI, which is artificial intelligence. So these days, AI is kind of a buzzword, and you hear it all the time, but without really knowing or referring to the mathematics underneath. So humans today are relying on smartphones and smart agents on devices for more and more types of services. So think about the speech recognition, which is necessary when you talk to your phone, if you actually dictate, emails or messages like I do. Or if you are interacting with a smart device like Alexa or Portal, which is the Facebook Meta device, you can ask it to play music, image recognition on your phone. There are apps which allow you to identify flowers or birds or things like that, which take in an image and make some kind of classification, identifying what it is. Directions, when you're traveling around trying to get directions, even things like music or movie recommendations on services that you may use, such as Netflix. But more importantly, and I won't have time to go into a lot of the applications, but there are a lot of kind of very serious applications where the outcome of the prediction or the classification has much bigger consequences than many of these recreational examples that I just gave you. So, for example, medical diagnoses, being able to take medical images and classify tumors, things like fraud detection for credit cards or banks, seeing a pattern of transactions and asking, the algorithms to detect transactions which are likely fraudulent. So there's all kinds of applications which are much more serious of AI as well. So what do we mean by AI? So AI, artificial intelligence, you can think of it as being like replacing the human brain with machines and machines' ability to learn. And so in computer science, we call this field machine learning. So for me, I often interchange the words AI with machine learning, ML. And this isn't quite fair, I know, because historically, many people think of AI, artificial intelligence, being more related to actually human intelligence and emulating, humans. But for me, and in practice and in connection with mathematics, it's a kind of a simplification to just equate it with machine learning. So whenever I say AI, I actually mean machine learning. So what is machine learning? Well, the way we set up a machine learning system is to decide on some mathematical model ahead of time. So there's a human in the loop, like a mathematician or a computer scientist, saying, okay, I'm going to decide to use this particular type of mathematical model, be that, the revolution recently in deep neural nets. So it could be something like a neural net, or it could be something much simpler like a linear means classifier, which I'm going to kind of explain here today. So once you've decided on a model, the two stages for AI or ML is, the first stage is that you feed data to this model in order to train the model. So the model, it has some structure to it, but it isn't trained specifically for your task or for your particular data set. And you train it by feeding a data set and adjusting the parameters of the model. So think of the model as being given by a bunch of coefficients. Maybe they are like scalar multipliers for different terms in your model. And by training the model, what we mean is determining what those coefficients should be. And then the second stage for machine learning is that trained models are used to actually make predictions or decisions or classifications. So in my examples above, for example, for image recognition, there would be models that are trained on many, millions of images of flowers. And then the classification task is, given a new image of a flower, can you predict which flower was the person looking at? So that I often refer to as the prediction stage. The first stage is the training stage. So training and prediction, those are the two stages for AI or machine learning. So there's a couple of things to note from a mathematical point of view. So one is, what I just described is what we call supervised learning, in the sense that when we were training, we fed the model a bunch of data or images. Let's stick with the example of classifying images of flowers that were labeled. So we had the image itself, and then we had a label. And so this is referred to as supervised learning, which is, you could say, maybe somewhat easier and simpler. And so I'm not talking here today about unsupervised learning, where your data would be a bunch of unlabeled data. And that's kind of a different problem. So secondly, I'd like to point out that a very important issue is that I've explained real world problems to you here, like images or preferences or a map, like for directions or medical images, things like that. In order for us to work on this data mathematically, all of this data needs to be converted into some kind of mathematical form, which typically is going to be vectors. So we actually have to take real world data and we have to convert it into vectors. So that means, first of all, you working with approximations of real numbers. So we'll have some amount of precision that we set that our system works with. And then we have to decide how to represent all of this data as vectors. So when you think of pictures, you can think of like all the pixels in the picture or a lot of other different types of representations. Like for robotics, we think about how do we represent a room? How do we represent real space as vectors? So it's very, very interesting questions and problems, even just starting with the representation of real world information, which I have encountered in my work in applications of cryptography. And I find that very interesting. Oh, sorry, how's my slides are not advancing. There we go. So I wanted to give you a specific example of some data represented as a vector. So here you have a question of doing prediction on medical data. So this was a real world example of some measurements that were made on tumors in patients. And there are a lot of different types of measurements that were made. So what you see is about 20 different columns here. And each column is a different type of measurement. And then you see like a floating point approximation to the measurement in each entry. And you can think each row here is one patient. So here's a collection of patients. And each of these patients had all of these measurements done. And then we also know for each of these patients whether the tumor was benign, which is green, or malignant, which is red. So given a very, very large amount of data like this, I've only shown you a very small selection of data points here, we can train a machine learning model. And then when a new patient comes in, we have to take all of these same measurements, create this vector, and then feed it into the model. And the model should give a prediction or a classification, whether they consider this tumor to be more likely to be benign or more likely to be malignant. So I like to use this example because it's very simple. It's a binary classification. So there's only two outcomes here, benign or malignant, red or green. In general, like the example of the flowers, there is many, many possible different flowers. So it's a more complicated classification problem. But just to give the idea of how AI works, I choose this kind of simple binary classification problem, and also a very simple model. So I'd like to just explain a linear means classifier. How does this work? Because it gives you a sense of the mathematics behind AI. How is mathematics used in machine learning and AI? So what we're going to do is, because as I mentioned, this is the supervised setting where we have labels for this data. We're going to divide the data into two categories. One are the ones that are labeled green, the other that are labeled red. And what we're going to do is we're going to compute the mean vector for each of these classes. And keep in mind, this is high dimensional. So I just showed you a table with about 20 different columns, so 20 dimensional, but it could be, you know, thousands of dimensions in, you know, medical setting. Or if you look in deep neural nets, you can have, you know, very, very, very high dimensional problems. Like when you're doing natural language processing, I thought working on hundreds of thousands of parameters was a lot, but now they're in the, you know, billions of parameters actually. So I'm just giving you a very simple example where we have about a 20-dimensional space, and you would compute the mean vector for each of your two classes. So the green class and the red class, and then you compute the difference vector between these means and basically compute the midpoint. You compute some kind of hyperplane that divides these two classes and separates them. Okay, so here I have a very lame picture to try to visualize here because I'm just showing you a 2-dimensional picture, whereas I just told you this is like 20-dimensional data. It's just that I can't really, draw a very nice 20-dimensional picture for you. So we're sticking with this just to get the idea. So think of the plane that separates this data as being now your classifier. Because given a new data point, when you're in the prediction stage, you would receive your new data point and plot it, and you would basically just decide which side of the hyperplane is it on in order to make your classification. So this is kind of the very, very high level oversimplified version of how AI works from the mathematical point of view. Because I gave you a very simple model here, the linear means classifier, you don't see like a lot of the complexity and a lot of the interesting and beautiful mathematics that goes into, much more complicated models. So just to try to explain the kind of the way it works in the more complicated setting, it's a generalization of what I've just explained, and that is, you're trying to compute a model, which is really just a decision boundary. So think of that hyperplane that separated the two classes. And in order to compute this, this boundary, what you do is you define a loss function, something like least squares distance, which given some, temporary version of the boundary, you're taking your data and you're computing kind of its distance to this boundary with more and more data that you're processing to train your model. And what you're doing is you're trying to kind of minimize some loss function. So the loss function is some measure of kind of how bad your model is. And you're trying to get this, you're trying to actually minimize this function kind of step by step. So the interesting thing here is that you could look at the process of not just defining the loss function, but actually minimizing this loss function as really just kind of advanced multivariable calculus and linear algebra, really. So there's a lot of interesting models and steps and loss functions and all kinds of considerations to think about, but at the heart of it, it's just really the mathematics that we learn in the first few years of an undergraduate mathematics degree is the foundation for being able to do AI in our society today. So I think that's a very wonderful connection. Of course, with that comes a great deal of responsibility to actually think about how this mathematics is applied and to try to create, responsible versions of AI. So that's the topic that I wanted to come to next here, which is that my background is that, well, I was actually a number theorist and algebraic geometer, but I moved into cryptography and coding theory when I was an assistant professor at University of Michigan. And then I moved almost entirely into cryptography when I went to Microsoft Research in 1999. So my field really is a crossover between mathematics and computer science, cryptography. And so cryptography is concerned with privacy, and I'll talk a little bit more about cryptography in the second part of my talk. But so the privacy problem is with AI is the next thing that I wanted to talk about. You could see from my description so far that you have to actually use a large amount of data in order to train models. And then also when you do a prediction, you have to use some data in order to apply the machine learning model and make a prediction. So both collecting, storing, and processing all of that data presents a number of kind of privacy and security challenges for anyone who's training models. And then for anyone who wants to use the models to get predictions, they have to share their data with the model in order to get the prediction. So why is this a privacy problem? Well, typically AI models or services are hosted in the cloud and maybe run by a smart agent, like I gave the examples in the beginning of Alexi or Portal or Cortana. So that means that all of this data is being uploaded to the cloud and processed there. So the question is, how do we actually protect data in the case that it is sensitive data, such as medical data or personal data, location data, financial data, all kinds of privacy issues. So I actually wrote about this in the ICMAM News in the spring, leading up to my Block Community Prize lecture in July. And so talking about some of the mathematics of cryptography that we can use to protect data while we're doing machine learning on it. So there's a new mathematical tool called homomorphic encryption, which can be used to protect data. And the really key thing about homomorphic encryption is that it works by actually operating on the encrypted data without decrypting it. So I like to give the example of Homer Simpson here, who's a jeweler and who put, if you want to outsource some work on your jewelry to this jeweler, but you don't trust the jeweler, you've got Homer Simpson here looking fairly surprised because he's being asked to work on this jewelry using this glove box that you see on the right. So he cannot actually access the gold. And the way it works is that you would put your gold inside of this locked box and give the jeweler the locked box, and they have to work on it in that locked box. But you keep the key, so you do not allow the jeweler to unlock the box. And when he's done working, Homer Simpson is going to give you back the box, and you have the key so you can unlock it. So that's the idea of homomorphic encryption is that you can take your data and you can kind of metaphorically lock it in a box. So the encryption key is what allows you to lock it, and you keep the encryption key. So you do not share it with the cloud service or whoever you're outsourcing the computation to. And when the computation is done and some prediction has been made, that is then returned to you, and you can unlock it by decrypting with the secret key that you keep yourself. So if anyone were to ask you, like at a cocktail party, what is homomorphic encryption? There's, instead of giving the Homer Simpson version of it, which I just gave you, you can say something much simpler, which is very short and very easy to say. Homomorphic encryption is encryption where you can exchange the order of computation and encryption. So you can either compute and then encrypt the value, or you can encrypt and then you can compute. And when you decrypt, you should get the same thing. So that's what homomorphic encryption is. And that's actually just by itself one of the key messages of this talk, just that we now have systems, mathematical systems for enabling homomorphic encryption. That's something that many people don't know and don't realize how practical they are for actually being able to handle sensitive data in encrypted form and do predictions such as machine learning. So that was kind of one of the key messages of my talk. So just to tell you a little bit more about homomorphic encryption, I worked for about 10 years of my career, roughly from about 2010 to about 2020 on homomorphic encryption, both defining new schemes and implementing efficient versions of it, building an open source homomorphic encryption library in my team at Microsoft Research and releasing it. And also improving the efficiency of these schemes, and then working on applications, primarily in health privacy and genomic privacy. And then finally showing in 2016 that we could even do deep neural net predictions on encrypted data. And in fact, real-time kind of human action recognition. So This fall, we had a paper in Nature Communications showing real-time encrypted video analysis that can detect falls on encrypted video streams. So just for me, this was a big chunk of my career, about 10 years of working on all different aspects of homomorphic encryption with a lot of collaborators and a lot of interdisciplinary projects, working with not just computer scientists, but researchers in bioinformatics and a lot of engineers to build real systems that can actually work in practice. So the homomorphic encryption library that I was referring to that we released in 2015 is currently still maintained by the team at Microsoft Research led by Kim Leine. We did an open source release of this in 2018, and we also built a standardization community to govern the use and parameters for homomorphic encryption. So if you'd like to download the software, please go to sealcrypto.org. Or if you'd like to see the standard, go to homomorphicencryption.org. So coming back to some of the mathematics, the new hard problems that the security of this homomorphic encryption schemes are based on go back actually to the 1980s. The lattice problems, well-known hard lattice problems such as the shortest vector problem and approximate shortest vector problem. But in the last 15 years or so, newer problems have been introduced that are related through security reductions to these hard lattice problems. So primarily the learning with errors problem, which I'll talk a little bit more about here today. So lattice-based cryptography, just a brief history, was proposed in the 1990s. Compared to some of the other public key crypto systems that are widely deployed today, such as RSA, based on the hardness of factoring, and elliptic curve cryptography based on the hardness of the discrete logarithm problem in elliptic curves, which go back to like the mid-70s and the mid-80s, respectively. So a bit older, but as you can see, lattice-based cryptography has been around for more than 25 years already. And the shortest vector problem that they're based on have been around even longer. So just like to point out that one of the advantages with lattice-based cryptography is that we don't currently have polynomial time quantum attacks on our lattice system. So that means that these systems are considered to be post-quantum secure, so far anyway. So this was essentially the first half of my talk, so I'll have to speed up a little bit in order to end on time here. But the first half of my talk was really trying to explain what is AI, how is mathematics used in AI, and at least one of the problems in responsible AI is privacy and protecting privacy for data, especially sensitive data. And so what I've explained here is a way that cryptography, in particular homomorphic encryption, can be used to protect privacy and security in AI systems. So that was kind of the first half of my message. So the second half of my talk is really about, well, AI is a new paradigm. Like I said, we're in a new era. I mean, AI is changing the world so fast in so many ways. So how is AI going to affect the security of crypto systems? So since going to Meta AI and it was Facebook AI research when I joined about 1.5 years ago, I started working with some new collaborators and interns and working on the question of how does AI affect cryptography. So very briefly, cryptography is the science of keeping secrets. So in particular, confidentiality of information, but also, which is achieved through encryption and decryption, but also authenticity of data, like digital signatures proving that you actually own the data that you claim that you own or that it's authentic. And then also for key exchange. So when you buy something online and you connect to the internet through a secure browser session, this relies on secure key exchange. So lots of different applications of cryptography that people use day to day without even realizing it: online banking and purchasing, private messaging. All of these kinds of e-commerce or online interactions are secured through crypto systems that have been standardized by various protocols. And I myself have worked on standardization at several points in my career. And so I find it to be a very interesting and important process. So for example, secure browser sessions are governed by like the SSL or the now TLS standard. Signed encrypted messaging and email is achievable through the ICMAM protocols. Virtual private networking through IPsec, and authentication through X509 certificates. These are just examples of some of the standards that govern our use of cryptography in the real world. So how do we actually gain public trust? Through this standardization process, which is typically open. There's a scientific community that includes researchers in academia, industry, and government coming together to make recommendations and then proposing specific standards, which are then drafted, made available for public comment, and then industry-specific regulations and standards are built on top of those. So it's a whole process. This is actually a picture of our homomorphic encryption standardization community in 2018 when we released the first standard for homomorphic encryption. And since then, it's been widely cited and referred to in government reports, such as in the UK, the Royal Society released a report on privacy enhancing technologies in 2019, referring to our standard. And there's ongoing work by the community, workshops and applications being developed. So just so you get an idea that the homomorphic encryption community is a very vibrant community. But the hard problems that cryptography relies on today, the homomorphic encryption is not yet widely deployed in industry today. The ones that are deployed today are based on the hardness of factoring and discrete logarithm problem in multiplicative group of a finite field and in elliptic curve groups. And all of these systems are known to be broken by a full strength, full size quantum computer that can do kind of computation and not lose fidelity. So if and when large scale quantum computers can be built, we will actually have polynomial time algorithms to attack all of the currently deployed crypto systems. So we really need to think about what's going to happen if and when a quantum computer can be built at that size. And so NIST has been working on this over the last 5 years, from 2017 to 2022. The National Institutes of Standards and Technology in the US has been running an international competition with teams from around the world to develop new post-quantum cryptography schemes, which really just means schemes for which we do not know any polynomial time algorithms to attack them on a quantum computer. So lots of different schemes have been proposed for standardization in the post-quantum crypto competition, including code-based crypto from the 70s, multivariate crypto systems from the 1980s, the lattice-based systems from the 90s, as I mentioned, and even one which I was involved in proposing, which is super singular isogeny graphs from 2005. So I'm not going to go into all of these systems now, if in the interest of time. But the question is, we need to see if these new systems are resistant to both quantum and classical algorithms. And so in particular for lattice-based cryptography, the rest of my talk, I'm going to talk about lattice-based cryptography. 2 of the 4 first quantum resistant cryptographic systems that were standardized in July of this year are based on lattice-based cryptography. So let me just get back to a little bit of the mathematics here. So what is a lattice? You can think of it as just a discrete linear subspace of Euclidean space. So here I've drawn it in 2 dimensions. you can actually just think of it as being generated by some set of basis vectors. So here I've given a picture of what I call a good basis. That's because the basis vectors are relatively short and they are kind of close to being orthogonal to each other. Whereas a bad basis, this is just 2 dimensions, so it's really easy, but just to give you an idea, a bad basis would be something where the vectors are much, much longer. So think of these vectors as having their endpoints like halfway around the world. And then also that they might potentially be very skewed. They might not be very orthogonal to each other. So the idea of lattice-based cryptography is that there is a hard problem here, which is finding short vectors or even finding the closest vector actually. And so the way that we use that hard problem is to define encryption schemes which add noise to a secret inner product. So you're going to have some random vector that's generated for each encryption. You have your secret vector, and then you have your message. And so the way you would encrypt is you blind your message by adding this secret inner product to the message. And if you only did that, you would basically end up with a system that could be broken just doing linear algebra. So what you do instead is to add a small error vector to each encryption. And so then the hard problem becomes to actually decode the error, really, to kind of remove the error, which ends up being what we call a bounded distance decoding problem, or it can be solved by solving the closest vector problem, basically finding the closest vector in a lattice and then attacking the system that way. So in other words, what I've just described to you is lattice-based cryptography and encryption based on the hardness of what we call learning with errors. That is, given a secret inner product plus noise. So I'm going to call it a noisy inner product with your secret. Given a bunch of random vectors and their noisy inner product with your secret, can you find the secret? That's the hard problem of learning with errors. So just think about it. You've got a learning problem, which is a bunch of these inner products, but if they're noisy, they've got error added to them. So it's learning, can you learn from these noisy inner products? So if you kind of recall the beginning of my talk, so think back to how I started this talk, was by explaining what is AI, what is machine learning. So machine learning basically assumes that you can learn from data. Given a bunch of data, you can learn from it. Even if the data is noisy, you can learn some kind of pattern, you can make predictions. That's the fundamental assumption of machine learning or AI. And also, it's interesting to think to the extent that it reflects, human intelligence and abilities as well. So here we are in cryptography, and we're making exactly the opposite assumption, which is given a bunch of noisy data, you cannot learn from it. That's the hardness assumption that the security of these lattice systems is based on. Of course, the devil is in the details in terms of what is the dimension of the system, how big is your error, how big is your kind of alphabet, the size of the modulus Q really matters a lot. But at a high level, it really begs the question, can we use machine learning to attack lattice-based cryptography? So that's the question I had in my mind for a number of years until I went to Facebook AI research, now Meta AI, and started working on this problem with my collaborators, so Francois Charton and Emily Wenger and Mingji Chen. So let me just tell you in the last couple of minutes what we actually did. So we focused on the problem for homomorphic encryption, where in homomorphic encryption, for efficiency reasons, we use binary secrets. So the secrets are just vectors of length n, which are just zeros and ones, and the error is small, but the dimension is very large. So we do this in order to increase the capacity for computation on encrypted data. So the dimension will be typically in the thousands.
So the NIST standards that I just mentioned, the lattice-based crypto systems that were standardized in the post-quantum crypto competition this summer, are based on different assumptions. That the dimension is typically much smaller, but the error is larger, and the secrets are random modulo Q for some prime modulus Q. So in our work, what we did was to attack LWE with sparse binary secrets. So we're really just presenting a new avenue, a new approach to attacking lattice-based cryptography here. We have not successfully broken any full-strength crypto systems yet. So we've only shown that this approach works for small to mid-size LWE problems, and that it may scale, but we haven't broken anything yet. But even the fact that it works is kind of surprising. So in the sense that because of the modulus Q, it basically requires that you can train machine learning models to do modular arithmetic, which we did quite a lot of experimentation on, and it is far from a trivial task. But even given the difficulty of learning modular arithmetic, we're still able to learn it enough to actually break LWE instances. So our approach is as follows. We set up a paradigm for training a model based on LWE samples, which we can then use as a way to extract secret predictions from the model. And then we use this secret verification to check whether the secret that we recovered is correct. So in other words, to check whether we broke the system. And as I said, we can recover secrets for small to mid-size LWE instances. And one of the important innovations and discoveries here in this work, which is actually appearing in November and December at the annual NeurIPS conference, one of the big machine learning conferences, is that, so the real discovery is that we can actually recover secrets even before the model has really started to learn very well. So just when the test loss starts to drop, we can actually start to recover the secrets already. So before the accuracy of the model goes way up, we can already recover secrets. So I encourage anybody who's interested to look at our paper, and which is on the archive. It's called SALSA, Attacking Lattice-Based Cryptography with Transformers, and it will be presented at NeurIPS this month. So overall, like my overall conclusion here is that the relationship between AI and cryptography, and there's, as you can see, a lot of mathematics in both fields, the relationship is very interesting because cryptography, on the one hand, can be used to protect data privacy and security in AI. But on the other hand, AI can be used to attack at least small versions of new post-quantum crypto systems. So we'll see whether it scales to attack larger versions. And also, I didn't get to talk very much about responsible AI, but responsible AI is an emerging field with many important challenges, including many mathematical challenges, or challenges that can be framed in a mathematical language. So my high-level message is really that I hope all of you young people out there really consider working in the fields of cryptography and AI and privacy, and applying your mathematical training in these fields. It's a very, very exciting time to be working in these areas. Thank you.
Thank you very much, Professor. Okay, any question for our speaker, the Professor Christie?
Okay.
Oh, okay. There is a question in the chat.
There is a question from Luz Marina.
Okay, Luz Marina, hi. How much it does affect the artificial intelligence to our daily life? In our daily activities, is it possible to live our life in terms of security without the artificial intelligence?
I'm sorry, I didn't quite understand the question and I can't see the chat, or maybe I can see the chat somehow.
Okay.
Oh, I see the chat now. How much does it affect the artificial intelligence? Oh, well, there's several questions here. Yeah, you can live your life however you want. You don't have to have a phone. You don't have to, drive a car, things like that. That's absolutely fine. You don't need artificial intelligence if you don't want it. Secondly, if you're worried about security and privacy with your artificial intelligence, then you should be worried. Because what's happening with these services as you use services on your phone, like when you download an app and then you allow that app to access the data on your phone, that means like your location, your photos, maybe your microphone, your camera, all these things that it asks you whether it can access. Then you're sharing your personal private data. Now that might not have any bad impact. It could be that your data is just put in with millions of other people's data to train models. You could argue in some settings that situations, this is good. We're providing valuable services based on a lot of this data. In particular, when I've spoken on this topic in medical settings, for example, communities fighting rare disease, people that want to see solutions to really rare diseases, they want data from all over the world to be pooled so that scientists can study that data so that you can train models and things like that. So there is definitely good things about aggregating data and learning from it and providing value, but there are potential harms if your data is compromised and some private information about you is leaked. Generally, people and companies that are handling data have very strict standards for privacy and security of data, and they're trying very hard to make sure that no harm comes to people, but it's a very hard problem. So the prototypical example of de-identifying data, even when it's been anonymized, was that I think it was like the governor of the state of Massachusetts in the US, that person's health data, health record was re-identified in a pool of health records that was being used for research. So it's just a question of the trade-off. And most of us who are using these services are daily making the decision to just go ahead and use these AI services, allow our data to be captured and used for training models, and not particularly worrying about the effects or dangers.
Okay, thank you. Milton.
Good afternoon. Do you think that artificial intelligence can lose control with quantum computing?
Thank you for the question, but I didn't quite understand something about quantum computing.
He's asking you if artificial intelligence could lose its control with quantum computing.
Yeah, so I'm not sure if I really understand what you're trying to ask, but I can make a comment, which is that, you could think about like combinations of quantum computing and machine learning. So I'm not sure if that was what the question is, but there are people that are thinking about that direction. I'm not particularly an expert on that.
Okay, thank you. Thank you very much, Professor. There isn't questions.
Maybe I have other question.
Other question.
Yes, maybe. What do you think about if our current devices are efficient for all the challenges that the artificial intelligence has in this idea?
Yeah, so actually, I think that it's a pretty amazing accomplishment of humans recently to make these artificial intelligence systems very efficient. So the fact that we're able to train models on billions of parameters and to actually apply them these models to make predictions in real time, to do image processing or even automatic speech recognition so well is a really amazing achievement. But the efficiency comes not just from the mathematical innovations, so algorithmic improvements, but also from the engineering collaboration. So that's something I've gained a huge appreciation for throughout my career, is the value of interdisciplinary work and working together with engineers who can actually help to design robust and usable systems that are also efficient. And like, for example, parallelizing computation, none of this would be possible without the power of parallelization. A lot of other different innovations from engineering, which are super important. So that's for the AI side. And then same thing for cryptography. For years, I worked on the efficiency of crypto systems and making them, real time, and homomorphic encryption in particular. People think it's wildly impractical, but we're able to show very complex computation, like I said, in real time, such as analyzing encrypted video stream, things like that. So there's a lot of work to be done on this efficiency side of things for crypto as well. But a lot of that's one of the main things that crypto researchers work on is efficiency. So both from the mathematical and the engineering point of view. So both AI and crypto are efficient today in the sense that they're being used and systems really are real time. The question is whether the combination will become efficient. So as I've argued, we can do AI algorithms in encrypted form on homomorphically encrypted data, and it's relatively efficient, but there are limits to what we can do. And then the other side of it is, can we efficiently attack crypto systems with AI? That's what we're working on. We're trying to understand how our attack scales up to larger dimension and whether it scales to be better than currently known attacks. So,
okay, thank you very much. Maybe I have just one comment. It's not about your talk, but I am part of the organizing committee, also Milton, Kari, and Brian. Our intention with this kind of event conferences is to show young people, people that is starting their studies in mathematics, to see which are applications, let's say, of mathematics in real world, and to see the different kind of mathematics that the people is working now. So my question is, if you have some recommendation for the young people, for young researchers or for young students that start their careers and maybe feel a little bit scared about moving in the world of applications, what you can say to these people?
Yes, definitely. Actually, in the past, I was often on kind of career panels at math conferences, which unfortunately I don't have time for anymore. But when I was with colleagues from other, industry and government jobs as well, there was a very consistent set of answers that we were giving to young people at the time. This is even 10 or 15 years ago. So training yourself to be able to do coding, so some level of programming. I think in mathematical research, that's becoming more and more useful as well, to be able to program. So it doesn't really matter, Java, C, Python, R, whatever it is that you want to use. Like in number theory, we have Paris for doing number theoretic computation, but to be able to program, number one. Number two, statistics. Statistics is underrated in mathematics. Statistics is super important preparation, both for understanding the world and for working in applications. And three is machine learning, actually. And even that's why I tried to show it to be a very accessible field that you can quickly learn with a mathematical background. So you can go online. There's Coursera courses. I actually, more than 10 years ago, started learning about machine learning just by taking Andrew Ng's Coursera course at Stanford. So Andrew Ng, NG is his last name. I think it's the most popular course on Coursera. So I think you can learn it that way. So I highly recommend learning machine learning, statistics, and programming.
Okay, so thank you very much. So on behalf of the Colombian Mathematical Society, let's say thanks to the Professor Lauter for her talk.
Thank you. Muchas gracias.
Okay, so our next speaker is Harald Helgoff. Let's see. Professor Helgoff, are you there? Yes. Ajá.
¿Me escuchan? ¿Me escuchan bien o no?
Te escuchamos muy bien, profesor, sí.
Sí, tengo también un micrófono, ese es el micrófono de mi laptop, tengo también un micrófono bonito, pero no sé cuál es
muy
preferido.
bien.
¿Está bien o no?
Okay, se oye muy bien.
Ah, bueno, entonces nos quedamos con este.
Okay.
Ok.
Y voy a compartir pantalla.
Muy bien.
Por favor.
A ver, uy, ¿cómo comparto? Estoy tratando de compartir. ¿Qué es esto de Use System Capture? A ver. ¿Ya ven mi pantalla o no?
Sí, sí, señor.
Ya, muy bien. Perdón. No vean mi Python. Miren, yo también programo, pero este fue por accidente. Un momentito. ¡Ah! Se me ha metido. La programación me está invadiendo. Un momento. Un
Ok.
ratito. Ya, estamos bien. Estamos bien.
Ok. Antes de darle comienzo al profesor, nosotros preparamos un pequeño discurso. Él será dicho en español y en inglés como antes. We prepare a small speech. It will be said in Spanish and English as before. Ok. Desde el país con la montaña arcoíris de América Latina y una de las mejores cocinas del mundo, Perú, me hace feliz anunciar hoy a uno de los mejores matemáticos latinoamericanos y del mundo, Harald Helgoff.
From the country with the Rainbow Mountain of Latin America and one of the best cuisines of the world, Peru, makes me happy to announce today one of the best Latin American mathematicians of the world, Harald Helgoff.
De una familia de académicos que conocía su gran potencial en las matemáticas, comenzó su contacto con la misma en sus primeros años de vida. En su juventud, Helgoff iba a la Universidad de San Marcos y a la Universidad Católica de Lima a estudiar en grupos de estudio para prepararse para las Olimpiadas Internacionales de Matemáticas. Todo su esfuerzo dio sus frutos cuando consiguió una beca para ir a la Universidad de Brandeis, en Estados Unidos, a hacer su licenciatura en Matemáticas y Ciencias de la Computación, abriendo así la puerta a todas sus metas como matemático.
From a family of academics that knew his great potential in maths, he started his contact with math at his first years of life. In his youth, Helgoff used to go to San Marcos University and Catholic Lima University to prepare himself to the International Mathematical Olympiad. All his work paid off when he got a scholarship to go to Brandeis University in the United States to do his bachelor's in mathematics and computer sciences, opening the door to all his goals as a mathematician.
En 1998 comenzó su doctorado en la Universidad de Princeton, bajo la dirección de Henryk Iwaniec y Peter Sarnak. No contento con esto, Helgoff fue profesor asistente postdoctoral de Gibbs en la Universidad de Yale del 2003 al 2004. Luego fue becario postdoctoral en el CRM y SM, Universidad de Montreal, de 2004 al 2006. Desde el 2006 hasta el año 2011, Helgoff fue profesor titular y luego rector de la Universidad de Bristol. Desde el año 2010...
Sí. Reader, es simplemente una especie de profesor, es todo, sí.
Ah, ok. Desde el año 2010 ha estado investigando en el CNRS, Center National the Research Scientifique, la organización de investigación más prestigiosa de Francia, ya que es la mayor agencia de ciencia fundamental de Europa. Inicialmente como investigador senior de primera clase en la École Normale Supérieure, disculpa ahí por la pronuncia, antes de convertirse en director de investigación de segunda clase en el Institut Mathématique de Jussy en el año 2014.
In 1998, he started his PhD at Princeton University under the direction of Henrik Iwanek and Peter Sarnak. Not happy with that, Helmut was a postdoctoral assistant professor at Yale University from 2003 to 2004. And then he was a postdoctoral fellow at ICMAM University of Montreal from 2004 to 2006. From 2006 to 2011, Helmut was a professor, a senior professor, and a reader at the University of Bristol. Since 2010, he has been researching RS, the most prestigious research organization in France, since it is the largest science agency in Europe. Initially, as a first-class senior researcher at the École Normale Supérieure and director at the Institut Mathématique de Jussy in 2014.
También ha tenido contacto con Alemania desde sus inicios, ya que estudió en el Colegio Alexander von Humboldt en Lima, Perú, y desde el año 2015 hasta el 2022 fue profesor Alexander von Humboldt en la Universidad de Göttingen. No es una sorpresa que domine el alemán, el francés, el inglés y por supuesto el español. Estas habilidades pueden ser tan impresionantes que también habla esperanto, fluido, ruso, griego clásico, intermedio ambos, y quechua, polaco, conocimientos básicos y actualmente está aprendiendo más idiomas.
He also has had contact with Germany since his early times, since he studied at Alexander von Humboldt School in Lima, Peru. From 2015 to 2022, he was an Alexander von Humboldt professor at the Göttingen University. It is not a surprise he's fluent in German, French, English, and Spanish, of course, and his multilingual skills are awesome, that he also speaks Esperanto, fluent Russian, classical Greek, intermediate, Quechua, Polish, and currently he's learning more languages.
Y si crees que has escuchado muchos datos impresionantes sobre el profesor, me gustaría decirte que es la única persona en el mundo que tiene el honor de decir que demostró la conjetura débil de Goldbach y que su prueba es ampliamente aceptada.
And if you think you have heard a lot of impressive data about Helmut, I would like to say you that he's the unique person in the world that has the honor to say he proved the Goldbach with conjecture.
Ok. También cuenta con varios premios y reconocimientos como el de miembro de la Academia de Ciencias de Göttingen, el de Fellow de la Sociedad Matemática Americana, ser miembro honorario de la Sociedad Filomática de París, doctor honoris causa en la Universidad Nacional de Córdoba, Argentina, la Cátedra Alexander von Humboldt, Fundación Humboldt en el año 2015, la Cátedra Gabriel Lamé, Francia, Rusia, Universidad Estatal de San Petersburgo, ser ponente invitado en el ICM 2014, Corea, profesor honorario en la Universidad Nacional Mayor de San Marcos, Lima, Perú, miembro correspondiente de la Academia Peruana de Ciencias, el premio Adams en el año 2011, Universidad de Cambridge, el premio Whitehead en el año 2010, Sociedad Matemática de Londres, y el premio Philip Levenhulme en el año 2008.
He also has several prizes and recognition as the member of the Göttingen Academy of Sciences, the Fellow of the American Mathematical Society, being an honorary member of the Société Polymathématique of Paris, a doctor honoris causa at the National University of Córdoba, Argentina, the Alexander von Humboldt Professorship, In 2015, the Gabriela Mecher St. Petersburg State University, being an invited speaker at the ICMAM 2014 in Korea, honorary professor at the National University Mayor of San Marcos, Lima, Peru, a corresponding member of the Peruvian Academy of Sciences, the Adams Prize in 2011 from Cambridge University, Whitehead Prize in 2010, London Mathematical Society, and Philip Lieberholm Prize in 2008.
Profesor, para nosotros es un honor tenerlo aquí. Muchas gracias por haber aceptado la invitación. Puedes comenzar.
Bueno, muchísimas gracias por todo y por leer todo mi currículum y exagerar todo logro que haya tenido alguna vez en la vida, pero concentrémonos en las matemáticas. Pero es realmente un gran placer ser invitado y me gustaría estar en este momento en Colombia, pero no estoy. Estoy en Göttingen y estoy hablando por Zoom. Entonces les voy a hablar de grafos expansores y de una aplicación a la teoría de números, una aplicación muy reciente. No, comencemos desde el principio. ¿Qué cosa es un grafo expansor? ¿Me escuchan bien, verdad?
Sí, señor.
Perfecto.
Ya. Miren, la intuición, el sentido intuitivo de qué cosa es un grafo expansor es bastante simple. Un grafo es expansor si está muy bien conectado. Y ese hecho es interesante si el grado es pequeño. Ahora voy a tener que formalizar qué cosa es el significado de todo esto. Y para comenzar tengo que definir qué cosa es un grafo y qué cosa es el grado. Eso sí es fácil de explicar. Un grafo, bueno, la mayor parte de ustedes lo conoce. Uno define un par, B y E. Ustedes ven cuando estoy escribiendo en la pantalla, ¿verdad?
Sí, señor.
Sí. V es un conjunto, para nosotros siempre es un conjunto finito, y E puede ser un subconjunto del conjunto de pares, o también podría ser, si es un grafo no orientado, un subconjunto del conjunto de todos los conjuntos con dos elementos en V. Pero digamos que es orientado, aunque siempre estaremos trabajando con grafos simétricos, en los cuales es como si fueran orientados, porque tenemos que V, W está en E, si solamente cuando uno cambia el orden todavía estamos en E. Ya, eso es muy abstracto. V, un conjunto de pares, pero los grafos se pueden dibujar de manera muy bonita, porque lo que yo puedo hacer es, yo pongo un punto para cada elemento de V, y luego yo voy a dibujar una rayita entre, digamos, si V y W, si este es un par en E, yo voy a dibujar una rayita entre V y W. Y ese es mi grafo, ¿no? Puedo poner unas flechitas si estoy trabajando con pares ordenados, como aquí, pero como dije, mi grafo va a ser simétrico, así que va a haber siempre flechitas en las dos direcciones. Es como que toda calle es de doble vía y podemos omitir las flechitas si queremos. Entonces, para dibujar un grafo, lo dibujamos así nomás, rayitas entre puntos. ¿Y qué es el grado de un grafo? Para comenzar, ¿qué es el grado de un vértice? Alguna gente la llama valencia, como en la química, y eso le dice a uno qué cosa quiere decir ya, ¿no? Porque la valencia del carbono es 4, la valencia del hidrógeno es 1. Es decir, ¿cuántas rayitas salen de un punto? Un punto sin rayitas es de grado 0. Un punto vértice con una rayita es de grado 1. Un punto con dos rayitas, es decir, un punto que figura en dos elementos de E, es de grado 2 y así y así. Y ese es el grado de un vértice. El grado es el número de vecinos en el grafo, ¿no? Este vértice es de grado 3. Este vértice tiene dos vecinos de grado 2, ¿no? Un vecino, otro vecino. Ya, y decimos que un grafo es de cierto grado si todos sus vértices son de ese grado. Entonces se habla de un grafo regular. Voy a repetir la palabra después. Ahora bien, ya expliqué qué cosa es un grafo y qué cosa es el grado de un grafo. Bueno, ¿y qué queremos decir con muy conectado? Que tiene un sentido intuitivo, pero ¿qué quiere decir? Eso se puede formalizar de varias maneras distintas, que al final son básicamente equivalentes, aunque no es nada evidente. Una es la definición combinatorial, Para comenzar voy a tener que definirles qué cosa quiere decir el conjunto de frontera de un cierto conjunto de vértices. ¿No? Ya les dije que los vecinos de un vértice son los puntos que están conectados a él por una rayita. Ya, ¿y cuál es la frontera de un conjunto de ese vértices? Miren, si yo tengo este conjunto de vértices, estos azules acá, mi frontera consiste en los vértices que no son azules, que no están en ese, pero sí están conectados a ese por una sola raya, por una sola arista. ¿Cuáles son esos? A ver, este punto está en la frontera de los azules. Los azules son estos. Los voy a poner en un circulito para que estén bien claros. Estos de acá y ese de acá también. A ver, entonces, ¿cuál es la frontera? ¿Este vértice está en la frontera de los azules? ¿El de acá? No, no está, porque no está conectado solo a este, que es negro, no es azul. ¿Ya? Entonces ese no está. Pero este de acá sí está conectado por un vértice. Entonces sí forma parte de la frontera. ¿Este forma parte de la frontera? No.
No.
¿Este forma parte de la frontera? Sí. Este también y este también. Y entonces esa es la frontera de mi conjunto. ¿Ya? Bueno, entonces decimos que nuestro grafo es un epsilon expansor, siempre hay que precisar el epsilon. Si para todo S tenemos que el número de puntos en la frontera, el tamaño de la frontera, ¿no? Estas rayitas no son valor absoluto, sino que quieren decir número de elementos del conjunto que es entre las rayas. Decimos que el grafo es epsilon expansor si el número de puntos de la frontera es por lo menos epsilon por el número de puntos en el conjunto. ¿Ya? Es decir, todo conjunto que sea de algún tamaño mínimo por lo menos va a tener una frontera grande. Incluso un conjunto pequeño va a tener una frontera grande relativa a su tamaño. Siempre, digamos que epsilon es un medio, la frontera de todo conjunto de vértices va a ser por lo menos, si epsilon es 1 sobre 10, la frontera va a ser por lo menos 10% del tamaño del conjunto. Podría ser más, pero por lo menos 10%. Y aquí tengo la condición de que sea esta condición tiene que variar simplemente para todo ese que tenga la mitad de los vértices. Porque claro, no podría tener truco, uno podría decir que ese es el conjunto de todos los vértices. Entonces la frontera está vacía. ¿Ningún grafo es expansor? Bueno, mejor excluyamos el caso de S igual a todos los vértices o igual a todos los vértices menos 1 o 2 o ese tipo de cosas. Y en verdad no hace daño poner esta condición solamente cuando S tiene por lo menos tiene a lo más la mitad de los vértices. Ya, y así es la definición combinatoria. Podría dar también una definición probabilística, un poco más informal, aunque se puede formalizar. Con la norma del infinito, podremos entrar a detalles. Ya, digamos que tenemos aquí un matemático. Digamos que se acabó el COVID, se abaratan los pasajes y nos podemos reunir todos en persona. Y después de la conferencia, la gente va a tomar unas aguas. Y un matemático que ha tomado demasiado. Entonces ahí solito trata de volver al hotel. Y bueno, comienza a hacer su marcha aleatoria porque no tiene la menor idea de dónde está yendo. ¿Ya? Entonces, aquí tiene dos caminos, entonces toma cualquiera de estos dos con prioridad un medio. Y aquí está tratando de ver, toma otro camino, cualquiera de esos tres, con la misma probabilidad. Digamos que se va para acá. Y aquí nuevamente podría volver marcha atrás, el pobre no tiene la menor idea, pero digamos que va para acá y luego de vuelta. Ya, esa es una marcha aleatoria. En cada vértice, en cada paso, nos vamos a cualquier vértice vecino con la misma probabilidad. Ya. Y bueno, decimos que nuestro grafo es un epsilon expansor si una caminata aleatoria equidistribuye a este pobre matemático muy rápidamente, después de pocos pasos. ¿Qué quiero decir con pocos? Bueno, no podrían ser menos del logaritmo de v, sobre todo aquí que el grado está acotado, pero digamos que queremos decir 1 sobre epsilon por logaritmo de v. Esa va a ser mi definición de pocos pasos. Y si después de esos pocos pasos, realmente la probabilidad de estar en cualquier lugar de donde fuera, en cualquier lugar de Colombia o no, digamos, cualquier lugar en Lima, es la misma o casi la misma, entonces decimos, este grafo de hecho es un expansor. Ya, y bueno, luego de la definición espectral, que es muy, muy útil, se requiere recordar un poquito de análisis funcional, o un poquito, o álgebra lineal avanzada, como fuera el caso. Vamos a definir, nuestro universo son las funciones que van del conjunto de vértices a los complejos. Y yo voy a definir un operador lineal sobre este espacio de funciones. El operador de adyacencia. ¿Qué cosa es este operador de adyacencia? El operador lineal es una máquina que da una función, le da otra función. Y de manera lineal, es decir, respecta la suma, la multiplicación por escalares. Y bueno, ¿qué hace este operador de adyacencia? ¿Qué cosa es esta nueva función, addf? Addf, su valor en V va a ser la suma de los valores de f en todos los vecinos de V, ¿ya? Y es un operador muy bonito, en parte porque si el grafo es simétrico, y como les dije, nosotros siempre trabajamos con grafos simétricos, tenemos un operador simétrico. ¿Qué cosa quiere decir operador simétrico? Les hago recordar que eso quiere decir que f ad g, para f y g cualesquiera, funciones cualesquiera, es lo mismo que si pasamos a de f para g. ¿Y cómo defino este producto escalar? Bueno, de la manera bastante usual. ¿Vale? Simplemente voy a poner 1 sobre n aquí, no porque importe, sino porque es cómodo. La normalización. Ya. Bueno, y si yo tengo un operador simétrico lineal, alguien me puede decir algunas cosas muy bonitas que son ciertas de los operadores simétricos lineares.
Que el espectro es real.
Exacto. Tiene este hermoso espectro real. Y bueno, no solo que es espectro real, todavía lo que es todavía más bonito, ese sí es útil, pero hay una cosa todavía más bonita, que el teorema espectral vale. Tenemos que va a haber una base una base lineal para este espacio de funciones, compuesta de funciones propias, ortogonales entre sí, por cierto. Es decir, que su producto es 0. Y si quieren, las ponemos todas de norma 1. Bueno, tenemos esta base ortonormal. Y ahí van sus valores que ordenamos, ¿no? Por orden, como los valores propios son reales, los ordenamos de manera descendiente. Ya, es fácil ver, en verdad es muy fácil ver, lo pueden hacer ahora mismo en la cabeza, que si nuestro grafo es regular, es decir, si el grado de todos los vértices, como decía, es el mismo, digamos, D, entonces el operador add va a tener una autofunción con autovalor igual a D, que es el máximo autovalor que podría tener. ¿Cuál? Bueno, cualquier función constante puede fungir de esto. Una función constante va a ser un autovalor, una autofunción, perdón, un autovalor D. ¿Por qué? Si yo tengo que cada persona aquí en el pueblo tiene exactamente de vecinos y tengo este operador que hace que, digamos, lo que yo voy a tener mañana va a ser la suma de lo que mis vecinos tenían. Entonces, y todo el mundo comienza teniendo lo mismo, si es una función constante, entonces después de ese cambio, todavía todo el mundo va a seguir teniendo lo mismo, simplemente multiplicado por el número de vecinos. Lo mismo que, bueno, no puede ser plata porque no se multiplica, COVID, por ahí. Mejor no nos metamos en el COVID. Demasiada gente ha sufrido, pero de hecho que los grafos y los autovalores y los autovectores son útiles para ese tipo de cosas, pero quedémonos en las cosas bonitas. Ya. ¿Qué cosa pasa con los otros autovalores? ¿No? Por definición, En verdad es fácil ver que es uno lo más D. Y bueno, esta va a ser mi nueva definición de expansor. Un grafo regular de grado D es un epsilon expansor espectral, y bueno, he añadido bilateral, porque es una definición un poquito distinta que no es, entre comillas, bilateral, pero no importa. Es un epsilon expansor. Si el valor, si todo otro valor, no el de la función constante, pero todos los demás son menores que D y por un cierto margen. Si son menores que 1 menos epsilon por D. Y lo de bilateral es porque para facilitarme la vida voy a poner que no solo es que lambda es menor que 1 menos epsilon por D, sino que el valor absoluto de lambda es menor que 1 menos epsilon por D. Ya, esa es la condición, esa es la definición de expansor espectral. En verdad, no es difícil, es un ejercicio, no para hacerlo ahora mismo, a menos que se estén aburriendo mucho, pero lo pueden hacer en la casa, que si yo tengo un epsilon expansor, un expansor espectral es un expansor en el sentido geométrico, bueno, combinatorio, lo hemos llamado combinatorio. Poco importa que lo llame geométrico o combinatorio, en el sentido combinatorio. Ya, les puedo dar unas pistas si quieren comenzar a resolverlo mientras que hablo. Lo que se podría hacer es proceder por contradicción. Digamos que no es expansor espectral, pero no es expansor combinatorio. Habría un S con frontera muy chiquita. Entonces ustedes traten de construir una contradicción a la suposición a partir de ese conjunto S y de su función característica, la función que toma el valor 1 dentro de S y 0 afuera. Y bueno, eso no resulta de inmediato, pero si uno le sustrae una constante, un múltiplo de una función, de la función que es 1 en todas partes, ya sale algo que da al final una contradicción a ser expansor espectral. Bueno, esa es una pista, si quieren lo pueden hacer. También uno obtiene, sin tanta dificultad, a partir de la definición de expansor espectral, que se trata de un expansor probabilístico. Si quieren llamarle probabilístico. Es lo del matemático borracho que les expliqué. Y bueno, lo que es más sorprendente y más difícil, bueno, tiene nombre, es lo que se llama desigualdad de Cheeger. La probaron Tanner, Alon y Millman, pero se inspiraron de un resultado que para mí es más complicado porque no soy del área de Cheeger, un resultado en la geometría. La desigualdad de Tanner, Alon y Millman dice que si yo tengo un epsilon expansor combinatorio, es decir, que la frontera de todo conjunto de vértices es grande relativo al conjunto, entonces tenemos un expansor espectral. Eso no es un ejercicio, eso hay que aprenderlo y no lo vamos a ver ahora, lo pueden ver está bien explicado en varios libros. Y mejor explicado en algunos artículos.
¿En qué
Ya.
libros, por ejemplo? Perdón, a los que no somos.
Bueno, hay una prueba en el libro de Tao, de expansores. Es un libro muy bonito. Bueno, sobre todo, es, en verdad, no quiero, encima creo por ahí te resta la audiencia. A mí me gusta, aún más que el libro, me gusta el blog de Tao. Porque el libro, básicamente, todo lo que está en el libro de Tao estaba en su blog. Y en el blog hay comentarios, hay enlaces. Y en verdad la prueba que da Tao, me parece que hay una complicación innecesaria, y eso lo dije en la crítica que escribí al libro de Tao en Mathematical Reviews. Pero es correcta, la que tiene es correcta, simplemente se puede simplificar un poco. Y también hay un artículo de expositorio, donde creo que Alon mismo es uno de los autores, si recuerdo bien. Y allí está también, hay otra explicación muy bonita. Sí. Bueno, a ver, estoy yendo a buen paso, entonces puedo decirles por cultura general que es esto la desigualdad discreta de Chigger. Lo voy a opcional, no tiene nada que ver con lo que vamos a hacer, pero vale por cultura general. Eh, es- si uno comienza, si uno tiene una superficie, creo que es para superficies bidimensionales, por ahí se hace también en dimensiones superiores, no sé. Giga. Creo que una superficie riemanniana, pero no voy a jurar. Y yo tengo que en esta superficie no hay cuellos de botella, es decir, no hay como estos, bueno, un cuello de botella, es decir, una parte que está unida al resto de la superficie solo por una pequeña región. Eso equivaldría a ser expansor combinatorio porque se trataría de una parte que tiene frontera pequeña. Imagínense en esto en tres dimensiones, ¿no? Es una superficie y es un cuello de botella es literalmente eso. ¿Tengo una botella por acá? No, no tengo, pero se imaginan, ¿no? Este es un cuello de botella. Y yo tengo, si tengo una superficie allí, entonces se puede mostrar que el laplaciano no tiene autovalores muy pequeños. Más allá, positivos muy pequeños, porque el cero también es autovalor. Bueno, entonces, históricamente eso se probó primero, y estos de Alon y Millman se probó después. Ya. En verdad, Alon y Millman yo creo que es de los años, se me olvida, 80 probablemente, pero no juro. Los expansores fueron definidos dos veces, porque era la época de la Guerra Fría y la gente no leía necesariamente, no publicaba en las mismas revistas, sobre todo en matemáticas sí, se traducía bastante, pero quizás no lo mismo en publicaciones aplicadas, porque Kolmogorov y Barsin fueron los primeros en definir los expansores en Rusia, y luego, unos años después, de manera independiente, Pinsker los definió también, no de la misma manera, pero de una manera equivalente, les dio el nombre expansor. Y la definición, como pueden ver, se trataba de cosas muy aplicadas. La motivación original venía de construir buenas redes de comunicación, ¿no? Porque un grafo, como dije, un grafo expansor, la intuición es que es un grafo de grado reducido. Bueno, es interesante con ese grado reducido, pero es un grafo expansor, es un grafo muy bien conectado. Entonces sería una buena red de comunicación si estamos allí con cable o con pita o con lo que fuera. Pero bueno, en verdad es lo que la gente siempre dice y históricamente es correcto, pero no es como se utilizan expansores en la práctica. La gente de telecomunicaciones encontró sus propias soluciones medio empíricas y no tiene necesidad de estas cosas aparentemente. Pero muchas veces cuando un concepto abstracto es definido, sale de una aplicación y luego esa aplicación se va, pero aparecen otras aplicaciones, ya sea en el mundo real o en la matemática o en los dos. Eso muestra que era la abstracción correcta, es una abstracción fructífera. Y fue el caso de los expansores. Ahora hay muchísimas aplicaciones de los grafos expansores. Tenemos muchas en la computación teórica, a códigos de corrección de errores, a la de randomización. Bueno. Y también hay mucho en lo que es grupos y geometría, ¿no? Parte de la teoría algorítmica, pero también el crecimiento en los grupos. Hay conexiones mucho con grupos infinitos. Y bueno, y eso tiene mucho que ver con ciertas propiedades de grupos aritméticos y bueno, mejor no me meto en los detalles, pero es un campo muy interesante, con fuertes conexiones con la teoría de números, sobre todo por las formas modulares. Ahora bien, las aplicaciones directas de los grafos expansores a la teoría de números no son tantas. En verdad, yo conozco una, la criba afín de Sarnak, y la conozco, es muy bonita, pero la conozco en parte porque yo estuve medio en ese baile también, porque Sarnak tenía la máquina de criba afín, pero le faltaba el motor, y el motor salió de Burgan Gamburg, que probaron que muchos grafos que vienen de la teoría de números o que tienen conexiones con la teoría de números son grafos expansores, y eso ellos lo probaron utilizando algo que yo había probado acerca del crecimiento en estos grupos. En los grupos se trata de grupos, el caso difícil y más útil es el caso de los grupos finitos. Y bueno, ya eso se sabe para otra gente también lo está generalizando. No solo yo, ha habido bastante otra gente. Bueno, mejor nos vayamos por las ramas, pero digamos que debido al trabajo de bastante gente sobre grafos expansores, se llegó a, a poder aplicar lo que se llama la criba fin. Pero no nos vayamos para allá. Allí hay también bastantes artículos divulgatorios que uno puede encontrar fácilmente, ¿no? Criba afín se dice affine sieve. Parece que la mayor, sí, no sé si hay tantos artículos en castellano, pero hay bastantes artículos en inglés. Y bueno, ahora no voy a hablar de eso, voy a hablar de otra aplicación, de una nueva aplicación de la teoría de números. Pero primero les voy a dar un poco de motivación. ¿De qué familia de problemas voy a estar hablando? ¿Tengo cuánto tiempo? ¿Me quedan 20 minutos?
25 minutos, si quisiera.
Fácil, yo creo que voy a dar 20 y después podemos tener preguntas.
Bien.
Dependiendo de... Si quieren puedo entrar en más detalles después al final, siempre me pueden pedir. A ver, hagamos una pausa, concentrémonos en otra cosa. Hay algunos problemas muy bonitos de promedios y autocorrelaciones. Están muy ligados con la teoría, con la distribución de los números primos. Se me olvidaba, voy a definir esta función que nos dice mucho acerca de la estructura fina de la factorización de un número. Porque ¿qué cosa es esta función? La función de Liouville. Es la función que en un producto de K primos, no necesariamente distintos, le va a dar a 1 menos 1 a la K. Es decir, es la función que toma el valor, la función sobre los enteros, que le da a 1 si el entero n tiene un número par de divisores primos y menos 1 si es un número impar de divisores primos. Contados con multiplicidad. Es decir, si lambda de 2 por 3 sería 1, pero lambda de 5 al cuadrado por 7, el 5 cuenta doble, entonces eso sería menos 1. Ya, esa es la función de Liouville. Y la función de Liouville es una función difícil de estudiar y ciertas operaciones muy simples resultan ser equivalentes a grandes problemas en la teoría de números. Por ejemplo, uno puede preguntarse, ¿qué es más común? ¿Que sea 1 o que sea menos 1? ¿Que el número de divisores de primos de un número sea par o impar? Resulta que en el límite el promedio es 0, es decir, que 1 es tan común como menos 1. Pero eso no es nada fácil. Eso es equivalente al teorema de los números primos, que fue básicamente el clímax de la teoría analítica, el ápice de la teoría analítica de números en el siglo XIX. Y es lo que se estudia, es muchas veces la meta central de un primer curso de posgrado de teoría analítica de números. Ya, bueno, hicimos el promedio, ahora vamos a sacar la autocorrelación. Porque, no, como nos dijo Chris en la otra, muchos conceptos de la estadística que son esenciales y uno de ellos es el de la autocorrelación. No, es lo que hago cuando yo comparo lambda de n con lambda de n más 1. Yo voy a sacar el producto y el promedio de ese producto. Esa es una autocorrelación. Como para decir, ya, si n tiene un número par de divisores primos, eso hace que sea más o menos probable que n más 1 tenga un número par de, de divisores primos. Y se cree que no tiene nada que ver, que el lambda de n sea 1 o menos 1 no está correlacionado con que el lambda de n más 1 sea 1 o menos 1. Y bueno, es lo que se cree, entonces el promedio de esto sería 0. El límite cuando x al infinito de 1 sobre x por esta suma sería 0. Pero ese es un problema abierto y muy difícil. Es lo que se llama la conjetura de Chauvet en grado 2. Está completamente abierto. Es de dificultad comparable a, digamos Goldbach fuerte o primos gemelos. O por ahí vamos. La conjetura de primos gemelos es que hay un número infinito de primos p tales que p más 2 es primo. ¿No? Esas conjeturas son de dificultad parecida. Ya, no hay mucha esperanza. Pero bueno, por el momento, en los últimos años ha habido muchos desarrollos increíbles realmente en toda esta familia de problemas difíciles. Algo muy bonito que se hizo, a mí me impresionó de hace 7 años, probado por Kaisa Matamaki, que ella está en Finlandia, y Rajivil, Maxim Rajivil, que está en California y Texas. Ellos probaron, eran muy jóvenes en la época, que lo siguiente es cierto, que, a ver, ya en la época ya se sabía que no que el lambda tenga, por ejemplo, algo que no sabemos y que probablemente y que no se va a saber probablemente hasta que se consiga la hipótesis de Riemann, es que si yo tomo un intervalo corto, por corto quiere decir que va, digamos, de x a x más raíz cuadrada de x, es decir, corto relativo a su comienzo, y yo saco el promedio de lambda y, que el promedio me va a salir aproximadamente 0. Eso todo el mundo lo cree, pero probarlo es otra cuestión abierta. Pero lo que sí se sabe es que en promedio, en la mayor parte, o en una proporción que tiende a 100%, de todos los intervalos cortos, y por corto quiero decir de longitud raíz cuadrada de x, cuando comienzan en x, o incluso x a la 1/6, está bien también, pero no menos de eso. En la mayor parte de esos intervalos cortos, el promedio va a ser muy pequeño. Pero nadie podía bajar a o más abajo de un x a la 1/6. Y Matomaki y Rashiviev fueron mucho más abajo, lo cual realmente era algo inesperado. Lograron ir hasta x a la epsilon. En verdad, lograron ir hasta el logaritmo de x, hasta logaritmo de x. Ellos probaron que si uno tiene cualquier función h de x que tiende a infinito cuando x va al infinito, dada una función así, uno puede probar que lambda de n tiene promedio 0, o que tiende a 0, perdón, en una proporción que tiende a 100% de los intervalos de longitud h entre x y 2x. H simplemente tiene que ir al infinito, pero puede ir muy lentamente al infinito. Bueno, y usando eso tuvo todo tipo de consecuencias, y una de ellas fue probada por Tao, quien probó, usando Matomaki y Rajiviev, una versión débil de la conjetura de Chauvet. Es lo siguiente, si uno saca un promedio, pero de manera un poco particular, dándole más peso a los n's pequeños, de esta manera, entonces el promedio Tao sí logró mostrar que el promedio era 0. Ya, la prueba de Tao, bueno, eso suena casi chiste. ¿Cuál es la idea de la prueba? O más bien dicho, la técnica principal de la prueba es lo que se puede llamar exhaustión de entropía. Es una técnica que existe más de una manera u otra en la combinatoria aditiva. También entiendo que la gente de computación teórica conoce cosas así, pero nunca yo había visto, y yo creo que no ha habido una prueba en teoría de números así. Era una técnica que era poco familiar para mucha gente. Y es una técnica que es poderosa, pero al mismo tiempo da cotas, bueno, a veces ninguna, pero en este caso se puede hacer que dé cotas, pero son muy malas. ¿Ya? Porque, por ejemplo, para lo que obtiene aquí interpretado como el límite, 0, lo que obtiene él es que esta suma dividida por logaritmo de x está acotada por está acotada por una constante dividida por logaritmo, 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 logaritmo de x. Es decir, logaritmo de logaritmo de logaritmo de logaritmo de x. Eso vale infinito cuando x vale infinito, pero vale infinito muy lentamente. Y hay otras cosas que uno podría decir. Propiedades un poco desafortunadas del teorema que vienen de cómo fue probado. Una prueba que fue, por otra parte, innovadora en el área. Bueno, entonces tratemos de aproximarnos a este resultado. Tratemos de probar este resultado, pero de manera más fuerte y mediante otros medios. Ya, aquí vamos a definir un grafo en teoría de números. Finalmente volvemos al tema que comenzamos. Pueden haber pensado ustedes que yo me había perdido, pero estamos volviendo a la teoría de números. Yo había definido un grafo que tiene como vértices los enteros entre n más 1 y 2n. Para un n grande. Y P va a ser un conjunto de primos hasta un cierto h. Bastante más pequeño que n, pero no diminuto. Por ejemplo, tau tenía que trabajar solo con primos que fueran a lo más logaritmo de n. Nosotros no tenemos necesidad de nada tan estricto. Y esas son las cosas que nos permitirá trabajar con mayor flexibilidad y obtener resultados más fuertes. Y bueno, esos son los vértices. Los enteros entre n más 1 hasta 2n. ¿Y qué cosas son las aristas? ¿Cuáles van a ser las aristas? Yo voy a conectar dos vértices con una rayita, es decir, con una arista. Sí, solo si la longitud de esta arista, P, es un primo en P y P divide a N. ¿No? P divide a N y por lo tanto también divide a N más P. Bueno, es este grafo. Y resulta que ese grafo es equivalente a un grafo definido de manera un poquito más complicada de mi punto de vista, pero equivalente. Con el cual trabajaron ya matemáticos y Tao, ¿no? Ellos probaron que ellos podían probar que ese grafo, en la mayor parte de las vecindades de ese grafo, ese subgrafo, esa vecindad era conexa. Y eso ya tenía consecuencias muy interesantes. Nosotros vamos a probar mucho más. ¿Qué es lo que quisiéramos probar? Y para comenzar, ¿por qué ese grafo nos interesa? Es fácil mostrar, y eso lo mostró Tao, pero en verdad lo pueden también, es básicamente, se podría hacer como un ejercicio con pistas, que si yo tomo el producto interno de lambda con el operador de adyacencia de gamma aplicado a lambda, y esto me sale, y ese producto interno es pequeño comparado con L, la suma de los recíprocos, es decir, si esto es cierto para algún P, para algún conjunto de primos P, con H no demasiado grande, entonces la conclusión va a valer, la conclusión que queremos, chaula débil va a valer. Solo tenemos que probar esto, que lambda, ad de lambda tiende a 0. Bueno, ¿cómo es que podemos probar tal cosa? Ya, Tao mismo veía que había una conexión entre esto con los grafos expansores. Lo dice de manera muy somera y un tanto, digamos que está metido en los comentarios y no da detalles, pero él dice que quizás pueda ser posible estimar expresiones de esta forma, quiero decir con esta forma, bueno, el producto interno de acá, quizás sea posible estimar expresiones como esta, estableciendo algún tipo de propiedad de expansión en grafos. Pero él no lo hace porque no lo pudo hacer. Es lo que dice, porque no tenía las técnicas, los métodos no estaban, según él. Pero yo digo que sí se puede. Vamos a comenzar con un modelo ingenuo. Para comenzar, ni siquiera está tan claro qué tipo de propiedad de expansión es aquí, porque este grafo, por ejemplo, ni siquiera es regular. Entonces no va a ser la definición espectral clásica. ¿Qué definición nos puede ayudar? Ya, podemos... va a haber un barullo con lo que correspondería al autovalor D, que no está allí porque las funciones constantes no son un autovector, porque el grafo no es regular, pero eso nos lo podemos quitar de encima poniendo un modelo ingenuo del grafo. Modelo gamma prima con un peso 1 sobre P en toda arista. Es decir, uno no pone la arista solo bajo condición que n y n más P, bajo la condición que P divida n, uno siempre le pone una arista muy débil de peso 1 sobre P, siempre, pero el peso es 1 sobre P, no es 1 jamás. Ya, y vamos a trabajar con el operador A, que es la diferencia entre estos dos operadores de adyacencia. Y quisiéramos poder probar que A no tiene autovalores grandes. Esa sería nuestra propiedad de expansión espectral modificada. O un primer intento de modificación. ¿Por qué? ¿Por qué es que eso nos ayudaría? Porque entonces tendríamos que el producto interno de lambda con A lambda tiene que ser pequeño. Porque va a ser pequeño para cualquier función. Va a ser siempre menor o igual que... Si no tiene autovalores grandes, si todos los autovalores son menores o igual que epsilon, entonces ese producto interno va a ser a lo más epsilon por la norma L2 de lambda. Pero como lambda tiene valor absoluto constante 1, esa norma L2 es 1 y eso es epsilon. Es decir, el producto interno de lambda y a lambda es menor que epsilon. Y también sabemos que el producto interno de lambda con A gamma prima el modelo ingenuo, A gamma prima el operador de adyacencia del modelo ingenuo con lambda, eso es menor, eso es pequeño. ¿Cómo es que lo sabemos? Eso se puede probar mediante las técnicas de matemática trivial. En verdad, lo que vamos a hacer es disjunto de matemática trivial, pero nos va a dar una consecuencia muy bonita porque lo podemos combinar con matemática trivial. Y en verdad, esta desigualdad fue probada y aportada basándose en matemática trivial, mediante métodos que sí son estándar. Entonces, lo que podemos hacer, si esto es pequeño y eso es pequeño, la suma también es pequeña. Pero la suma no es sino nuestro viejo amigo, ad gamma. Tenemos entonces que lambda, ad gamma, lambda, es a lo más epsilon más epsilon prima. Es decir, es pequeño. Y eso es precisamente lo que queremos probar, ¿no? Porque esto, saber que eso es pequeño, nos dará chaula débil. Y en verdad nos da varias otras cosas, como veremos. Ya. Lamentablemente, esto que quisiéramos probar no es exactamente cierto. ¿Verdad? No es cierto. Los culpables son los vértices de muy alto grado, porque hay entero, si bien un entero de tamaño n tiene en promedio logaritmo de n factores primos, es decir, no muchos, hay algunos vértices con un grado muchísimo mayor, y algunos enteros con muchísimos más divisores primos que eso, y eso arruinaría todo el espectro. Si un vértice tiene grado de grande, tiene que haber un valor propio de tamaño por lo menos raíz cuadrada de y si es enorme, raíz cuadrada de enorme es enorme. Bueno, se acabó. También algo más útil es que hay bastantes ciclos cortos y es decir, maneras de salir a pasear y volver a donde uno comenzó. Hay demasiados y esos también como que embarran el espectro. Pero podemos excluir estos vértices de muy alto grado porque hay muy pocos. Y también excluyendo unos pocos vértices podemos excluir todos los ciclos cortos. Parece un poco extraño, desconfiable, pero en verdad es una de las partes más fáciles. Y bueno, podemos excluir estos culpables porque son pocos y aún obtener que ad gamma es pequeño. No realmente ad gamma, sino la reducción de ad gamma a un conjunto X con complemento pequeño. Y eso es lo que hicimos. Y he aquí el teorema que tenemos en nuestro artículo, que estoy reescribiendo, pero bueno, pueden ver la primera versión en el archive, que existe un número pequeño de vértices, Y, los culpables que dije y unos pocos más, tales que para X, el conjunto de los otros vértices, la restricción de AX tiene una propiedad de expansión fuerte. no solo es que todo autovalor es menor que 1 menos epsilon por el grado promedio, no es solo que todo autovalor es menor que epsilon por el grado promedio. ¿Y cuál es el grado promedio? No es sino nuestro amigo L, la suma de los recíprocos, sino que todo autovalor es a lo más una constante por raíz cuadrada de L. ¿Ya? Eso es algo tan fuerte cualitativamente hablando como se puede esperar. No se puede probar algo que sea mucho más pequeño que raíz cuadrada de L. Es como quien dice cualitativamente Ramanujan. Los grafos Ramanujan son los expansores más fuertes y solo está un factor constante de distancia. Y bueno, les podría dar la definición todo de manera más técnica y precisa, pero yo creo que está claro así como está. Simplemente, bueno, la restricción es lo que uno podría imaginarse, que uno primero aplica F a la restricción, luego uno le aplica el operador A y luego uno aplica la restricción nuevamente. Ya, esa es la restricción. ¿Y qué pasa? Que por como hemos excluido pocos vértices, todas estas consecuencias bonitas todavía no salen. Y de esa manera logramos probar nuevamente chabla débil, pero con cotas mucho mejores que las de Tao. Porque nos sale que la autocorrelación de lambda con esta cuestión logarítmica, con estos pesos, 1 sobre n, es a lo más c sobre raíz cuadrada de logaritmo de x, que es lo más que se puede esperar de este grafo, porque L es de tamaño como logaritmo de x, y bueno, como les dije, uno no puede obtener algo mejor que raíz cuadrada de L. Entonces, si se logra probar una mejor cota, tendría que ser por otra ruta, ¿no? U otro grafo, por lo menos. Entonces, como les dije, Tao y Travaine habían llegado a logaritmo. Y aquí tenemos logaritmo. Bueno, no solo eso, sino que se puede probar cosas acerca de la estructura fina de lambda que no se podía probar mediante los métodos de Tao. Por ejemplo, uno puede estudiar no solo los números que tienen un número par de factores primos, uno puede estudiar los números que tienen exactamente un número dado de divisores primos. Cierto número dado de divisores primos. Y entre ellos, los n con exactamente parte entera del logaritmo de n, lambda n más 1 es tan probable que sea 1 como menos 1. ¿No? Ese es un resultado bastante delicado y no se podía llegar a él mediante lo que había probado acá. Bueno, he aquí lo principal de lo que quería decir. También he preparado algunas cosas acerca de la prueba. No nos da realmente el tiempo como para una prueba. En una charla de coloquio generalmente no hay tiempo, pero podemos hablar de eso o de otras cosas que les interesen ahora en la cuestión, el tiempo de preguntas. Ahora mismo es un buen punto del cual terminar.
Creo que sí, profesor.
Entonces terminemos
Estaríamos
aquí.
justo a tiempo.
Tengo algunas transparencias más o puedo escribir impromptu si quieren saber más de la prueba o de aplicaciones o cualquier otra cosa. Entonces pongamos punto seguido aquí. Preguntas.
Muy bien, profesor, muchísimas gracias por la charla. Pues ahorita vamos a dar espacio a ver si alguien del público quiere hacer alguna pregunta.
Ok, podría iniciar con una pregunta. Profesor, en este promedio, 1 sobre logaritmo y suma de lambda n por lambda n más 1, ¿se podría mejorar esa cuota si en vez de poner ese peso de dividir entre n, uno escogiese un exponente más pequeño, un n a la 1 menos epsilon, dividir por algo más pequeño que n?
Muy interesante. Ligeramente, por lo menos, sí. Deja que lo piense un poquito. Ya, como consecuencia de eso sí se obtiene eso. Pero para un epsilon muy pequeño. Perdón, para un epsilon no constante. Dejen que lo piense un ratitín. Dejen que lo piense un ratitín. Es una muy buena pregunta. A ver. Y... A ver, tratemos de ver qué se rompe si no se hace eso ahí. ¿Qué se va a romper? Algo se va a romper. A ver. Yo creo que lo que va a pasar allí es que dejen que haga un pequeño calculito. Yo creo que ya veo dónde va a haber un problema.
Bueno,
Un ratito, denme un segundo. Ahora mismo les digo, ¿ya?
tome todo el tiempo que quiera, profesor. Esto es increíble.
A ver, 1 menos epsilon. ¿Cuál es el problema con 1 menos epsilon? Va a ser que ya les puedo decir cuál es el problema. El problema no viene en ninguna parte por acá, porque aquí no tenemos peso 1 sobre n o nada en ese grafo. El problema va a venir en este paso que les dije que era fácil, que viene de tau. Porque en ese paso se usa de manera crucial lo siguiente. Muy buena pregunta, por cierto. ¿Por qué no? ¿Por qué no trabajar de esa manera? Es porque en este paso ese paso de aquí utiliza el hecho que cuando tenemos esta medida, un intervalo cambia poco bajo multiplicación por un primo p. Un primo p no enorme, no de tamaño x, sino un primo p pequeño moderado. ¿Cómo así? Porque ¿qué cosa es lo que eso quiere decir? Si yo tengo un intervalo acá, de 1 hasta x, su medida, la medida de los enteros en ese intervalo va a ser esto, que es aproximadamente logaritmo de x. Ya, si ahora yo lo multiplico por p, me va a salir este intervalo, px. Ya, y esto le va a salir a 1. A ver, esto es básicamente el mismo intervalo, excepto por la parte que va de x a p sobre x y esta parte de acá que va entre 1 y p. Pero queda eso de allí. La suma de 1 sobre p para, no, de 1 sobre n hasta p, más la suma de 1 sobre n de x hasta px. ¿Esto qué va a ser? Esto va a ser aproximadamente logaritmo de p. Y esto que va, perdón, de x hasta px también va a ser aproximadamente logaritmo, porque eso es el logaritmo de P más logaritmo de Px menos logaritmo de X, eso se cancela y le sale alguno logaritmo de 2P. Perdón, P2 logaritmo, 2 logaritmo de P. Y entonces, como yo les dije, estamos trabajando con primos P, que son bastante más pequeños que X. No de minutos, pero bastante más pequeños. Entonces, 2 logaritmo de P va a ser pequeño comparado con logaritmo de X. Ya. Y entonces la pregunta es, ¿qué pasa cuando yo tengo, en vez de eso, una potencia, 1 menos epsilon? Bueno, allí vienen las lágrimas, porque si yo tengo esto de acá, eso va a salir aproximadamente 1 sobre epsilon, x sobre epsilon. ¿Ya? Pero la suma de lo mismo, de hasta p va a estar bien, pero la suma de lo mismo entre x y px va a salir ¿qué? Va a salir esto de aquí, que es aproximadamente 1 epsilon xp epsilon menos x epsilon. Ya, pero entonces le sale a 1 ese factor de p epsilon menos 1. Y eso va a ser, no va a ser, no va a estar, no va a ser pequeño, en verdad ni siquiera va a estar acotado. ¿Ya? Entonces no es pequeño.
Okay.
Esto de acá, esto no es pequeño comparado con... ¿Ya? Ese es el
Muchas
problema.
gracias. Muchas gracias. Increíble.
Vale, no sé si alguien más tenga alguna pregunta para el profesor Helgo. No. Bueno, listo, profesor, pues agradecerle por la charla, muy interesante, muy dinámica también, eh, muy interesante y pues espero que se haya sentido bienvenido aquí por nosotros.
Muchísimas
Y
gracias.
Y lo invitamos a participar, por supuesto, los días que quedan, en el momento en que tenga tiempo, pues ahí está
Sí,
la programación.
yo estaba siguiendo en YouTube nomás, pero bueno, voy a meterme en Zoom de ahora en adelante también. Uno puede
Gracias.
meterse en Zoom, no hay un límite muy estricto de personas.
No, no lo
Ya,
hay.
bueno, voy a seguir asistiendo en Zoom.
Muy bien.
Excelente, grande. Antonio Salazar, vamos a habilitar el micrófono. ¿Quiere hacer tal vez una pregunta, un aporte? Listo. Adelante.
Creo que dejó la pregunta en el chat.
¿Sí me escuchan? Porque
Ya.
apenas activó mi micrófono. Bueno, les decía que muchas gracias por todo lo que están haciendo. De verdad es admirable su trabajo matemático y creo que la comunidad matemática que están trayendo es increíble y muchas gracias de verdad por esta oportunidad. Y bueno, la pregunta sería, por qué le interesó la teoría de números? Y pues bueno, el resultado de la conjetura débil de Goldbach es bastante interesante porque es una continuación matemática de, bueno, desde el tiempo de Hardy y Littlewood. Entonces, lo que usted hizo es algo que ellos no pudieron hacer y me da muchísimo orgullo que usted sea de, bueno, de América Latina, ¿no? Pero mi pregunta va un poco en esa función de por qué entró a la teoría de números, qué fue lo que le atrajo de esta
Bueno,
bella.
para comenzar yo no lo veo como que hice, bueno, no lo hicieron, no lo podían hacer, era hace 100 años,
Sí, claro,
no lo veo como que yo los vencí, sino que yo estoy trabajando yo estoy parado sobre sus hombros, ¿no? Yo construí sobre lo que había hecho Vinogradov, que a su vez construyó sobre lo que había hecho Hardy Littlewood. Es como una casa de varios pisos. Es como que dije, tú hiciste los cimientos, yo hice el segundo piso, yo soy mejor que tú, ¿no? Si no funciona. Hardy Littlewood pusieron los cimientos, luego Vinogradov construyó la casa y luego yo estuve construyendo sobre los altos, ¿no? Sobre cómo me interesó la teoría de números, desde un principio, cuando era muchacho en el Perú, en la época era difícil conseguir libros de matemática en el Perú. Y era caro, pero habían esos libritos de la editorial Mir que sí eran económicos. Y a mí me regalaron por un amigo un estudiante que nos entrenaba para las Olimpiadas. Me regaló para mi cumpleaños el librito de Vinogradov, que el texto es muy simple, de elementos de teoría de números, pero los problemas son muy difíciles y muy interesantes. Y eso fue una de las primeras cosas que me hicieron interesarme por la teoría de números cuando yo era escolar. Y luego la seguí, aprendí otras cosas y más cosas. No estaba seguro cuando era estudiante universitario que yo fuera a hacer teoría de números, pero me di cuenta que en la teoría de números se aplica todo. Uno puede aprender muchas cosas en toda la matemática y no hay saber perdido. Todo al final es útil para la teoría de números. Y claro, también está el lado que la teoría de números tiene muchos enunciados simples de comprender, ah, pero que es muy difíciles de probar. Eso lo hace atractivo para muchos, pero para mí quizás fue más el hecho de que haya todos estos niveles de conocimiento en la teoría de números en los cuales entra todas las matemáticas. No es el único campo en el cual se puede decir tal cosa, pero yo diría que es un campo del cual se puede decir eso especialmente.
Perfecto, muchas gracias. No, y sí, simplemente decir eso de Littlewood y Hardy, no me refería a esa parte, sino que sí, más bien es como muy wow que haya continuado la matemática. Y una admiración total. Muchas gracias por su admirable respuesta. Y gracias a todos por esto.
Muy bien, muchas gracias. Bueno, pues entonces así cerramos con broche de oro este segundo día de conferencias. Los invitamos mañana a participar. Ya saben que el link es diferente. Todos tienen los links de todos los días y la transmisión en YouTube será mañana antes de las 7 de la mañana, hora Colombia. Ok. Entonces, buena tarde para todos.
Buenas tardes.
Ok.
Adiós, adiós.
Buenas
Chao.
tardes.
Bye bye.
Gracias.
Gracias.
See you tomorrow.